Today I'm doing a continuation of yesterday's class, Electrostatic Potential and Capacitance. Yesterday, let's do a quick recap about what I did yesterday. Any charge, if placed in a place, it will produce electric field, and in this electric field, any charge will have a potential. When we bring a charge from point R to P, we will need a certain amount of force. That force in NCERT, they took this force is equal in magnitude to the force due to the electric field QE. And the work done will also be equal to the work done by the electric field, and this work done will be stored as potential energy. And when the force or the external force on the test charge will become 0 and we release the charge, that is nothing but the force becoming 0, then the potential energy will be directly converted into kinetic energy. And we consider the potential at infinity to be 0, and potential is the work done per the test charge which we moved. Using the same formula, we get that using the formula that V equals W by Q, we also get that work done equals Q times V when potential is Q times V final minus V initial. It will become work done will become QV when this is 0, that is when the potential where the initial charge is at infinity. Only then we use this formula. Now the next topic is electric dipole, potential due to electric dipole. Potential due to an electric dipole. As we learned in the last chapter, an electric dipole consists of two charges, Q and minus Q, separated by a small distance 2a, equal and opposite charges separated by a small distance. Its total charge is 0. It is characterized by a dipole moment vector P, whose magnitude is Q times 2a, or Q times the distance between them, and which points in the direction from minus Q to Q. The dipole moment vector will point from negative to positive. This should be remembered. Let's read the statement again. An electric dipole consists of two charges, Q and minus Q, separated by a small distance of 2a. Its total charge is 0. Also a point to be remembered. It is characterized by a dipole moment vector P, whose magnitude is Q times 2a, and which points in the direction from minus Q to Q, which is negative to positive. We also saw that the electric field of a dipole at a point with the position vector R depends not just on the magnitude R, We also saw that the electric field of a dipole at a point with a position vector r depends not just on the magnitude of r but also the angle between r and p. We are saying the electric field of a dipole doesn't only depend on the vector or the position vector magnitude of the position vector r or the distance between the only. We can't just say it is just 1 by r square. This electric field doesn't depend solely on 1 by r square, where r is the magnitude of the distance. It depends also on the angle between r and p, where p is the moment vector, dipole moment vector. Further, the field falls off at large distance, not as 1 by r square, typical field due to a single charge, but as 1 by r cube. Here it does not depend on 1 by r square, but as due to a single charge, here we saw that here the electric field is depending on 1 by r square. This is for a single charge, but here in case of a dipole it is not 1 by r square but 1 by r cube. So this means that as the distance increases, the fall of the electric field is even more drastic. We now determine the electric potential due to a dipole and contrast it with the potential due to a single charge. We now determine the electric potential due to a dipole and contrast it with the potential due to a single charge. As before, we take the origin at the center of the dipole. Now we know that the electric field obeys the superposition principle, meaning if the electric field due to many charges is nothing but the vector sum of the individual electric fields. But since potential is a scalar quantity, the superposition for voltage or potential is the algebraical sums of the individual potentials. Since potential is related to work done by the field, electrostatic potential also follows the superposition principle. Thus, the potential due to the dipole is the sum of potential due to charges q and minus q. Here there are two charges, so it will be this. Let's see the diagram. At any general point P, this is the dipole, this is the distance, and the P vector pointing this way from negative to positive, and R1 is the distance from positive Q to the point P, R2 is the distance from minus Q to the point P, and theta is the angle, and the total dipole length is 2a. And the potential, we know it is 1 by 4 pi epsilon naught q by r, and if we take for the superposition, then it will be 1 by 4 pi epsilon naught for positive charge q by r1 plus 1 by 4 pi epsilon naught for negative charge minus q by r2. We can take 1 by 4 pi epsilon naught outside. So the final potential due to a dipole will be 1 by 4 pi epsilon naught q by r1 minus q by r2. As they give quantities involved in the calculation of potential due to dipole, which are the P vector, which is the dipole moment, the magnitude, I mean the position vectors. Pretty much that's all. Where r1 and r2 are the distances of the point from q and q minus q respectively. Now by geometry, r1 square equals r square plus a square minus 2ar cos theta. This is also, we can also get it from the triangle theorem, addition law, triangle of vector addition. Based on that, we know if we want to calculate r1, we get it as r1 equals root r square plus a square minus 2ar cos theta. And in the same way, r square here it is plus. This is the vector law of addition, triangular vector law of addition. We take r much greater than a, that they are saying that they will take the dipole length, or they will take that the dipole is a very short dipole, meaning the dipole length is very short compared to the distance from point P, or taking this as a point dipole, so thereby neglecting a and retain terms only up to the order in a by r. Here this term they neglected because a is already very small. A is already very small compared to r, and when we square a, then it will be even more smaller than a. A square is even more smaller than a, and once we divide it by r square, we are dividing it, means it's reducing even more. A square by r square, it is even more smaller than a square. So this value is extremely small, and even if we add it, it doesn't matter much. Because of such a reason, we take it equal to 0, and for a short dipole, we take that it is this. Similarly, r square 2 is approximately equal to 1 plus 2a cos theta by r. This is r1 square. Here the sign change, that's all. Using the binomial theorem and retaining terms up to the first order in a by r, we obtain 1 by r1 is approximately equal to 1 by r times 1 minus 2a cos theta by r whole power negative root, which is approximately equal to 1 by r 1 plus a by r cos theta. We can take, when a by r is a very small value, we can take this power inside, so we can write this as 1 by r1 approximately equal to 1 by r times 1 minus 1 by 2, this is the power, times when 2a by r is very small quantity, 2a by not by cos theta. Then 2 cancel, minus times minus, it will become plus, so the final answer will be 1 plus a cos theta. This is an approximation where the inside value, where 1 minus a power whole n, a is a very small quantity, we can write it as 1 minus n a. Believe this is the correct formula. That is what they did here. And this only happens because we take it as a point dipole or a very short dipole. And 1 by r2, similarly it will be 1 by r times 1 minus a by r cos theta. Using equations 2.9 and 2.13, 2.13 are these both equations, 2.9 being the equation that the potential is q by r1 minus q by r2, and P equals to QA, or Q times total distance. We get that V equals Q by 4 pi epsilon naught. I believe they substituted equations 2.13, both equations 2.13a and b in the equation here. Let's try. The value for 1 by r1, approximately they took it as 1 by r times one plus a by r cos theta, and 1 by r2 is approximately 1 by r times 1 minus a by r cos theta. Then if we substitute these values in this equation, well, we get the potential, and V equals 1 by 4 pi epsilon naught, where we take Q as well common, because the Q is just equal and opposite and not anything different. So we take Q outside, it will be 1 by R1 minus 1 by R2. So R1 is 1 by 1 plus A by R cos theta minus 1 by 1 minus A by R cos theta this, if we further simplify, V equals Q by 4 pi epsilon naught cross multiplication 1 minus A by R cos theta minus 1 plus A by R cos theta by, we can write it as 1 plus A by R cos theta, this is, I'll tell you, times 1 minus A by R cos theta, potential equals Q by 4 pi epsilon naught. This we can apply the signs here, 1 minus A by R cos theta minus 1 minus A by R cos theta, 1 minus 1 cancel, by, this is in the form of a plus b times a minus b. This formula equals a square minus b square. So we can write it as 1 square minus a by r cos theta whole square and in such a case v equals q by 4 pi epsilon naught minus 2 times a by r cos theta by it will be 1 minus a square by r square cos square theta. This a square by r square is a really small quantity, so we will neglect it. So it will be equated to 0. Then we get that v equals minus q, I took the minus outside, by 4 pi epsilon naught 2 a by r cos theta. This way can write it as v equals minus 2aq cos theta by 4 pi epsilon naught times r. We know that p equals 2a times q, so this value we can substitute it as p. So the potential equals minus p cos theta by r times 1 by 4 epsilon naught. I believe this is the final answer. This is r square I might have gone wrong somewhere, so this is actually positive. This is r square, so the final answer should be v equals p cos theta by r square 1 by 4 epsilon naught, where p is not magnetic dipole but electric dipole moment. R is distance from the center of the dipole, or as we consider the dipole as a short dipole, we need not consider it as from the center, but directly we can just say it is a distance from the dipole, because this is only for a really short dipole. And 1 by 4 epsilon naught is the k value, which is Coulomb's constant, and even in this constant epsilon naught is the permittivity of free space. This is the electric field, not electric field but the potential at any point due to a electric dipole. Now we can write this p cos theta equals p times r vector, where r, not r vector but r cap. R cap is the unit vector along the position vector OP. The electric potential of a dipole is then given by V equals 1 by 4 epsilon naught P r cap, P dot r cap, where this is the dot product. If there is a dot product with a vector, then that means there is cos theta there. So we need not mention it here. Where r is extremely bigger than the dipole length. This is the final equation. Or but if you want to solve normally when they give theta, this is the final equation where p cos theta 4 pi epsilon naught r square. This is if they gave in the vector form. Equation 2.15 is as indicated approximately true only for distances large compared to the size of a dipole. So that higher order terms in a by r are negligible. For a point dipole P at the origin, equation 2.15 is however exact. This is, as I said before, only for a point dipole, considering that the length of the dipole is only a point, is only like a point compared to the distance from the point outside. It will be a 2-minute break. let's continue. The final formula for potential due to dipole is V equals 1 by 4 pi epsilon naught, where times P cos theta by R square. We can write it in this form as well. R cap is the unit vector indicating the direction. By multiplying the R cap vector, we are not increasing the magnitude, because the magnitude of unit vector is 1 and 1 times anything will remain the same thing, so the magnitude is not increased, but the R cap is only indicating the direction. From this equation, potential on a dipole axis, theta equals 0 or pi, cos 0 is 1, cos 180 is minus 1. Because of that, it is potential equals plus or minus 1 by 4 pi epsilon naught P by R square. Positive sign for theta equals 0 because cos 0 is 1. Negative sign for theta equals pi because cos 180 degree is minus 1. The potential in the equatorial plane, theta pi by 2 is 0 because why in the equatorial plane? Equatorial plane meaning if we take a dipole of plus q and minus q, this is a dipole. If we take an equatorial plane, it is in this plane. In such a case, let's assume it's a point on the equatorial plane, some point x. At this point, if you find the potential formula is 1 by 4 pi epsilon naught q by r. This for a single charge, and you want to for a dipole, we will add the charges and the distance will be equal. This will be equal to this, so it will a distance r, let's assume. So 1 by 4 pi epsilon naught charge q by r, this charge, plus minus q by r, v equals 1 by 4 pi epsilon naught q minus q by r. So this will equate to 0, at 0 times anything is 0, so potential in the equatorial plane will always be 0. This is only the electric potential and not the electric field. Potential in the equatorial plane will be 0 because the distance will be same, and this is the case only for a dipole. Now let's continue. The important contrasting features of electric potential of a dipole from that of a due to a single charge are clear from equations 2.8 and 2.15. 2.15 is this equation where the potential of due to a single charge is V equals 1 by 4 pi epsilon naught q by r, but here it is a whole different formula for a point dipole. And as for the equation 2.8, it is the equation kq by r. If we see this equation and this equation and this equation, these two equations, we clearly understand the differences. The potential due to a dipole depends not just on r but also on the angle between the positive vector r and the dipole moment vector p. It is however axially symmetric about p. That is, if you rotate the position vector r about p, keeping theta fixed, the points corresponding to p on the cone so generated will have the same potential as at p. Basically what they're saying is, for a dipole plus q and minus q, the potential will depend on the angle theta. But if we take it as a 3D view, then on this axis, as taking this axis, taking the dipole as an axis where this angle is as well theta, or in this axis where the theta is fixed and all sides on the circumference on this axis, they will have the same potential. Taking this as the line of axis, and in a three-dimensional view, where theta is always fixed, it will not change. In points, let's assume A, B, C, D, the potential will be same. That is what they're mentioning here, as it depends on theta. But in case of, this is in case of dipole where it is only possible, it is only equal axially, but in case of a normal potential, no matter how it is in all the three dimensions, no matter which side, if the distance is same, be it in the z-axis, y-axis, x-axis, if the distance is same, the potential will always remain same. Because here there is no dependence on the theta, but here there is dependence, so it's only possible where they are equal in the axial plane. Yes. The electric potential falls off at large distance as 1 by r square, not as 1 by r. Characteristic of the potential due to a single charge. You can refer to 2.5 for graphs 1 by r square versus r and 1 by r versus r drawn in the other context. Electric dipole potential. Electric dipole potential. Potential due to electric dipole, not a normal potential for single charge. It depends on 1 by r, but potential due to electric dipole, it is inversely proportional to 1 by r square, because we see a formula here. It is r square. R square. Because of that, the potential due to dipole decreases way more as distance increases than a potential due to a single charge. Now the next topic, potential due to a system of charges. Potential due to a system of charges. Consider a system of charges Q, Q1, Q2, Qn with positions vectors R1, R2, Rn related to some origin. The potential V1 at P due to the charge Q1 is, let's see the diagram first. This is the superposition theorem we studied in the chapter 1. The same for this potential, where potential due to number of charges. Potential at a point due to system meaning a number of charges is the sum of potentials due to individual charges. Here, since potential is not a vector quantity, This is we can take as a scalar sum, but electric field is a vector quantity, so we should take a vector sum there. Here this is the point P. These are the numerous charges of Q4, Q2, Q1, Q3 and Q5 with position vectors R1P, R2P, R3P, R4P and R5P. And due to the potential due to a single charge is 1 by 4 pi epsilon naught Q1 by R1P, where R1P is the distance between Q1 and P. Similarly, the potential V2 at P due to charge Q2 and V3 due to charge Q3 are given by same equation, where R2P and R3P are the distances from P from charges Q2 and Q3 respectively, and so on for the potential due to other charges. By the superposition principle, the potential V at P due to the total charge configuration is the algebraic sum of potentials due to the individual charges. V total equals V1 plus V2 plus V3 plus dash 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 Vn, and as 1 by 4 pi epsilon naught is common, it is taken outside. If we have a continuous charge distribution characterized by a charge density rho, we divide it as before into small volume elements, each of size delta V, carrying a charge rho delta V. We then determine the potential due to each volume element and sum, strictly speaking, just integrate overall such contributions and thus determine the potential due to the entire distribution. We have seen in chapter 1 that for a uniformly charged spherical shell, the electric field outside the shell is as if the entire charge is concentrated at the center. Thus, the potential outside the shell is given by V 1 by 4 pi epsilon naught Q by R, where Q is the charge concentrated at the center, which is not actually true, where it is concentrated not at the center but on the shell, but we assume it to be concentrated at the center, where Q is the total charge on shell and the R is its radius. Capital R is its radius, but small r is the distance from the center to the point. The electric field inside the shell is 0. This implies that potential is constant. Inside the shell, because there is no charge, the electric field will be 0, but the potential will be finite or constant, as no work is done in moving a charge inside the shell, and therefore equals its value at the surface, which is 1 by 4 pi epsilon naught Q by R. Let's read this paragraph again. If we have a continuous charge distribution characterized by a charge density rho, charge density, maybe it is charge density rho equals normal density is mass by volume, maybe it is charge by volume. We divide it as before into small volume elements. If this is a continuous charge density, we divide it into small elements, each having a volume of delta V and carrying a charge, because here based on this formula charge equals rho V, and if we take a small charge, dq equals d rho V. We then determine the potential due to each volume element and sum. We integrate these values. Wait, no, we don't integrate these values. Here V is not voltage or potential, but it is volume. We then determine the potential due to each volume. If we take a formula, this is the formula. What they give, rho equals Q by V, and rho V equals charge, and dq equals d rho V, and potential equals, this is voltage, this is voltage, this is volume, and this is voltage or potential. Potential equals 1 by 4 pi epsilon naught Q by R. So in place of Q, we can substitute rho V, or integrate this and substitute the integrated value there in this equation. So 1 by 4 pi epsilon naught times the integrated value. If we take density as constant, it might come out dV, and if we have limits, then we can differentiate it. There might have been something wrong here, but it's okay. Basically they're just saying integrate. So we find the total charge density. No, not charge density, but the total potential. And the next topic here is a uniformly charged shell. A uniformly charged shell let's assume it is positively charged. This is a spherical shell having a radius capital R. In such a case, due to this shell, the potential at any point P outside, where it is distance from the center is small r, then the potential at point P, V at P equals 1 by 4 pi epsilon naught Q by small r, where Q is the total charge of the shell, and at any point inside the shell, let's assume it is here, they're assuming that if we move this charge inside this shell, it might be true that the work done is 0. If we move this charge from here to here, then the work done will be 0. So the potential inside will be equal to the potential at the surface. So we can write, this is not P, this is VP. V got here. Yes, VP equals, this is V at point P, then V at center of shell equals V at surface. This is because the work done in moving a charge inside the shell is like 0, and if that is the case, V at surface equals 1 by 4 pi epsilon naught Q by capital R, where capital R is the radius of the shell. This is what the second paragraph was saying. Let's see this. Two charges, 3 into 10 power minus 8 coulomb and minus 2 into 10 power minus 8 coulomb are located 15 centimeter apart. This is not a dipole because the charges are not equal in magnitude. It will only become a dipole when the charges are equal in magnitude and opposite, meaning different signs, positive and negative, located 15 centimeter apart. At what point do the line join the two charges is the electric potential 0? Take the potential at infinity to be 0. Let us take the origin O at the location of the positive charge. The line joining the two charges is taken as the x-axis, the negative taken on the right side. Based on this, the hint they gave in the question is that potential, if there are two charges, they gave 3 into 10 power minus 8 and 2 into 10 power minus 8 coulomb. And 2 into 10 power minus 8 coulomb. So at some point here, let's assume the potential is 0. That is what they gave. So let's assume the total it is 15 centimeter or 0.15 meter is. So let's assume this distance to be x and this distance from the negative charge to be 0.15 minus x. If such is the case, then the biggest hint is the electric potential is 0. Because of that, potential is 0. V equals 0 equals 1 by 4 pi epsilon naught into 10 power minus 8 pi, the distance from that point, and V2 equals 0 equals 1 by 4 pi epsilon naught 3 into 10 power minus 2 into 10 power minus 8 by 0.15 minus x. In such a case, since both are equal, equate them. Both are equal to 0. Equate these values. V1 equals V2. This equal to 0. Here we can indeed take 1 pi 4 pi epsilon naught outside. We can just send it this side and it will turn into 0. Let's do another method. Let's try if it works if we send this value to 0 as well. Let's send this side, so it will be 1 by x equals 1 by 0.15 minus x. No, it won't work. Let's Let's try in the normal method now, where V1 equals V2 then that will be 3 into 10 power minus 8 by x equals 1 by 4 pi epsilon naught 1 by 4 pi epsilon naught minus 2 into 10 power minus 8 by 0.15 times minus x and 3 into 10 power minus 8 10 power minus 8 cancel by minus 2 equals x by 0.15 minus x it will be 3 into 0.15 minus x equals minus 2x 0.45 minus 3x equals 2x 5x equals 0.45 x equals 0.45 by 5 5 ones are 0.9 meter 0.09 meter so let's see the value I got. The value I got it is 0.09 meters in the first case. In this case x equals 0.09 meters or 9 centimeters, but here we got it as 0.075. There is something wrong here, so the best way to do it is take potential as equal because both are equal to 0, cancel 1 by 4 pi epsilon naught, then you will get a value of the distance. The main parts in doing this question is guessing that the hint is v equals 0 and taking the distance as x and taking the other distance as a total distance minus x instead of taking it as another variable y. Okay. let's read the paragraph. This shows that V is a constant if R is a constant. Thus, equipotential surfaces for a single point charge are concentric spherical surfaces centered at the charge. Now, the electric field lines for a single charge Q are radial lines starting from or ending at the charge in case of the negative charge, and starting from the charge like this in case of a positive charge, depending on whether Q is positive or negative. Clearly, the electric field at every point is normal to the equipotential surface passing through that point. Basically, here, in case of a sphere, so single charge, radially outward, we take a sphere, this is always normal. Electric field lines are normal, meaning perpendicular to the equipotential surfaces This is in case of a single charge or single charge at the center, sphere or shell. It's not always true, but mostly. Now let's continue. This is true in general. For any charge configuration, equipotential surface through a point is normal to the electric field at that point. The proof of this statement is simple. If the field were not normal to the equipotential surface, it would have non-zero component along the surface. To move a unit test charge against the direction of the component of the field, work would have to be done. But this is in contradiction to the definition of an equipotential surface. There is no potential difference between any 2 points on the surface, and no work is required to move a test charge on the surface. The electric field must therefore be normal to the equipotential surface at every point. So basically what they are saying is, let's assume that the electric field for a circular object, a charge, this is the spherical equipotential surface, and this is the, let's assume normally general rule is that it should be perpendicular to the equipotential surface, but let's assume it is not perpendicular, meaning it is something like this. If we divide this electric field into two components of E cos theta and E sin theta, then let's place a charge here. If we want to move this charge from here to here, when there is here, if we place this on this equipotential surface, then let's assume it is not, the electric field is not perpendicular to the equipotential surface, and if we split it into two components, on this surface there is a E sin theta component which will push this charge, or this charge will experience a force of the E sin theta component, but there should be no work done, no force, no work done in moving a charge in an equipotential surface. But in such a case, we will indeed need work done to move this charge from here to here, because there is a E sin theta component. But that itself ruins the definition of the equipotential surface. Equipotential surface means there is no work done in moving a charge across a surface where potential is constant. If potential is constant, there is no work done in moving a charge in that surface. So here it is causing work done, so this is not possible. In that case, we can assume that E vector is always perpendicular to the equipotential surface. That is what the NCERT was saying. Equipotential surfaces offer an alternative visual picture in addition to the picture of electric field lines around a charge configuration. If the field were not normal to the equipotential surface, it would have non-zero component along the surface. To move a unit test charge against the direction of component of the field, work would have to be done, but this is in contradiction to the definition of an equipotential surface. There is no potential difference between any 2 points on the surface, and no work is required to move a test charge on the surface. The electric field must therefore be normal to the equipotential surface at every point. Equipotential surfaces offer an alternative visual picture in addition to the picture of electric field lines around a charge configuration. Equipotential surfaces for a uniform electric field. This is a uniform electric field, and these are the equipotential surfaces. For a uniform electric field E, say along the x-axis, let's assume this is a x-axis and this is the uniform electric field. The equipotential surfaces are planes normal to x-axis like this. When this is the x-axis, these are normal, meaning the planes are perpendicular to the x-axis. They are parallel to the YZ plane. Equipotential surfaces for A dipole and B two identical positive charges are shown in the figure. Equipotential surfaces for A dipole here. In case of a dipole, surrounding the dipole there are equipotential surfaces. Here as well, individually there are equipotential surfaces. This is for a dipole where there are two equal and opposite charges. This is in case of two positive charges close together. They are identical, meaning have equal charge. In such a case, it is like a dumbbell-like structure where the equipotential surface is formed. It's not perfectly circular, and this is the merging, we can say, of the both equipotential surfaces. That's it for that page. Now relation between field, electric field, and potential. Consider two closely spaced equipotential surfaces A and B. B and A. With potential values V, they have equipotential, meaning at any point on the surface B, the potential is same, and any point at potential A, at surface A, potential is same. But that doesn't mean potential at A and B is same. The potential at A surface is same and the potential at B surface is same. That's all. Consider two closely spaced equipotential surfaces A and B with potential values V, where V is the potential of V, and the potential of B surface is V plus delta V, where delta V is the charge in V in the direction of the electric field E, where delta V is the change in V, not charge, in the direction of the electric field E. Let P be a point on the surface B, here this point. Delta L is the perpendicular distance of surface from A to P. Imagine that a unit positive charge is moved along this perpendicular direction, perpendicular from surface B to surface A. Surface B to surface A, from here to here. A against the electric field, the work done in this process is E delta L. This is basically they are taking two surfaces here. Oops. Yes, two surfaces here. They are parallel to each other. They are parallel to each other. Oh, diagram is not really great, but so a sectional view, or another way of viewing this is one view. View 2 and view 1, two sheets of paper, you can assume. At this plane, the potential, this is the surface B and this is the surface A. This is the point P on the surface B, and the potential at B is V plus delta V, where delta V is a change in potential, and V, it is V. The potential at A, it is V. And if there is a charge which we move from B to A, and this is the perpendicular distance from A to B. If we move from here to here, the work done, the work done equals the potential difference. Why does that happen? They mentioned that it is a unit positive charge. Imagine that a unit positive charge is moved along the perpendicular from the surface B to surface A against the electric field. The work done in this process is E. So it is moved. The electric field is in this way, where it is, we can present it as this way. I just drawing the diagram, but let me draw it here again, representing the electric field. it is moving from this point. This B surface will have a lower potential than A surface because the electric field originating from some charge, and as A surface is closer to this charge, A will have a higher potential than B. Because of that, when we move a charge from B to A, the potential, the work done will be against this electric force. And we know the formula: force equals QE, and for a unit positive charge, force equals 1 times E. So force equals electric field for a unit positive charge, and we know that force times distance equals work done. So multiply it with the distance we are moving here. So force times L equals E times L. In such a case, work done equals E times L. And work done equals QV. So where it is a unit positive charge, it might be taken as W equals V equals EL. So V we can take it as EL. Is that how we got that formula? I'm not too sure, but that is how I think it is, basically for easy remembering as to how we got that formula. The work done in this process is E times delta L, because for a unit positive charge, in this case force equals E, at force times distance, E times distance equals work done. The work equals the potential difference. This work equals the potential difference, maybe because here W equals delta V. Here it is only V because the another one I took V initial equals 0 because V initial is at infinity. But if that is not the case, W equals Q times delta V, which is the difference in potential. So this is the actual correct formula. W equals QV only when the initial potential is 0 or the particle is said to be placed at a position infinitely far away from the final position. That is why they say work equals the potential difference. Potential difference means delta V, VA minus VB. Thus, E delta L, which is work done, equals negative of V minus V final, the potential at A, minus V initial, which is V plus delta V, equals negative of delta V. So we get the formula. Basically what they are saying is, let's derive the formula again. For a unit, this is strictly for a unit positive charge, meaning Q equals plus 1 coulomb. In such a case, where deriving the equation 1, first we need to derive how how work done equals E times L. That is the case because force equals QE, because we know that electric field intensity formula is E equals F by Q, and basically taking E this side, we will get force equals QE. In this formula, Q will be 1 because we take a unit charge, and when we multiply with distance, force times delta L. Delta is L is a change in distance. Here I took it L, but is actually delta L. In the diagram as well, this distance is not L but delta L, and force times delta L equals E times delta L, and force times delta L, force times distance, equals work done. So work done equals E times delta L. This equation is derived. Next, potential, the potential work done equals delta V. This we should derive basically the formula. At the starting we derived something like in the previous video, the total potential energy is equal to work done. The change in potential energy is equal to work done, because the work done may increase or decrease the potential energy, and this is for a two charge system or a many charge system, mainly two charge system itself. So if we divide it by Q, we get a special quantity called V. In such a case, it's actually delta V. Potential, in such a case, work done equals Q delta V, and Q in our case is 1, so work done equals delta V. This is the second relation. And for the third relation, which is E equals minus delta V by delta R, delta L. This how we got is, since in this equation we got work done equals E delta L, and in the other equation we proved that work done equals change in potential difference. Equate equation, since LHS here is equal, equate RHS here. So E delta L equals, we can write this delta as delta V. No. This is delta V itself, just delta V. Now delta V we can write as V final minus V initial. Then V final is, we are moving a charge from the potential of V plus delta V, which is the initial, to V, which is the final. So V final minus initial will be V minus V plus delta V. In such a case it will be V minus V minus delta V, plus V minus V cancel, minus delta V equals E delta L, and we get the final formula that electric field equals, for a unit charge, one more time, a unit charge minus delta V by delta L equals electric field. That is how we got very important relation between electric field and potential, which is used in numerous questions. Very important relation. How we got such a relation. This is strictly, once more, strictly for a unit charge. When we consider the charge we are moving to be a unit charge. So E equals minus delta V by delta L. Since delta V is negative, delta V equals minus of magnitude delta V. We can rewrite equation 2.20, this equation, as minus delta V by delta L, as if we take magnitude of E, You can write it as magnitude of delta V by delta L. We don't need to specifically mention plus here. It is just mentioned. With us are two important conclusions concerning the relation between electric field and of course potential. Electric field is in a direction which the potential decreases steepest, meaning electric field is in a direction which potential decreases steepest, meaning if there is a potential, if like the first point they are telling is, if let's assume the potential at this surface is 10 volt and at another surface is 5 volt, at another surface is 2 volt, and it continues to go on, and in this surface it is 0.2 volt, then if it is asked, they did not mention that, I'm not mentioning any distances. If you want to find the direction of the electric field, then it will obviously be in this direction. As the potential is decreasing the steepest, that is the side of the electric field. As there is low potential, that side it's the electric field. Another example where if this is 100 volt, example 1, example 2, 100 volt, another surface of 200 volt. We can take this not as surfaces but also points, but I am taking surfaces here because we are under the topic of equipotential surfaces. 500 volt, if the direction of the electric field is asked, it will not always be in this direction, but mostly the magnitude or the component or cos or sine component, mostly it will be in this direction. But in case if they ask actual direction of the component, then it will be this side. Electric field is this side. Direction of the electric field is this side, where the potential is decreasing. Electric field is in the direction of which the potential decreases the steepest. Its magnitude is given by the change in magnitude of potential per unit displacement normal to the equipotential surface of the point. Change in potential, basically this formula. It is given by change in potential per unit length. Change in potential, as the change in potential, as potential changes, how much it changes per some amount of length or per unit length, that is what we call as an electric field. And the next topic is potential energy of a system of charges. Potential energy in a system of charges. I will do this after a break of 5 to 10 minutes. potential energy of a system of charges. Consider first a simple case of two charges q1 and q2 with positive vector r1 and r2 relative to some origin. Let us calculate the work done externally in building up this configuration. This means that we consider the charges q1 and q2 are initially at infinity and determine the work done by an external agency to bring the charges to given locations. Suppose first charge q1 is brought from infinity to point r1. There is no external field against which work needs to be done. So work done in such a case, we are bringing single charge where there is no external influence, the work done will be 0. The external influence I am talking about is not the specific unspecified charge, that in unspecified force on the charge, but any opposing charge like the electric field. Because we are only bringing a single charge, there is no opposing force, so the work done is 0. This charge produces a potential in space given by the basic formula, where r1p is the distance at point p in space from location of q1. From the definition of potential, work done in bringing charge q2 from infinity to point r2 is q2 times the potential at r2 due to q1. Basically, they used a formula W equals QE. We are bringing charge Q2 and the potential at the specific point is 1 by 4 pi epsilon naught. This is the potential. So substituting this value in this equation, we will get that the work done on charge Q2 is 1 by 4 pi epsilon naught Q1 Q2 by R12. This is the potential energy or change in potential energy, where R12 is the distance between point 1 and 2. Since the electrostatic force is conservative, this work done gets stored in form of potential energy of the system. Thus, the potential energy of the system of two charges Q1 and Q2 is U equals 1 by 4 pi epsilon naught Q1 Q2 by R12. This is the figure. Potential energy of a system of charges Q1 and Q2 is directly proportional to the product of charges and inversely to the distance between them. Q1 and Q2, two charges, the distance is R12. Obviously, if Q2 was brought first to its present location and Q1 brought later, the potential energy U would be the same. More generally, the potential energy expression, equation 2.22, this equation is unaltered whatever way the changes are brought to the specific locations. If you bring Q1 first or Q2 first, the potential energy will always be same because of path independence of work for electrostatic force. Equation 2.2 is true for any sign of Q1 and Q2. If Q1 times Q2 is greater than 0, meaning positive, potential energy is positive. This is as expected, since for like charges Q1, Q2 greater than 0, electrostatic force is repulsive and a positive amount of work is needed to be done against this force to bring charge from infinity to finite distance apart. For unlike charges Q1, Q2, Q1 times Q2 smaller than 0, the electrostatic force is attractive. In that case, a positive amount of work is needed against this force to take the charges from given location to infinity. In other words, a negative amount of work is needed for the reverse path from infinity to present location. The potential energy is negative. Equation 2.2 this equation is easily generalized for a system of any number of point charges. Let us calculate the potential energy of a system of three charges Q1, Q2 and Q3 located at R1, R2, R3 respectively. To bring Q1 first from infinity to R1, no work is required. Next, we bring Q2 from infinity to R2. As before, work done in the step is Q1 V1 R2 1 by 4 pi epsilon naught Q1 Q2 by R1 R12. The charges Q1 and Q2 produce a potential difference which at any point P is given by work done in bringing Q3 from infinity is 3 times V1 to it. It's the final equation. So I'll derive it. Basically, for three charges, we use the formula for any charge. We use the formula Q delta V. If we first brought a charge Q1 from infinity to point origin, let's assume somewhere we brought this charge Q1 here, this work done will be 0. Next, we bring one more charge Q2 from infinity to this some point with a distance of R1. There will be some work done which we calculate by W equals Q2 times V final, which is 1 by 4 pi epsilon naught Q by R1 minus 0, because at potential at infinity is 0. So this is the work done. And for a third charge Q3 from infinity to a point, let's assume R2, then this will be work done equals Q3, we are moving, potential at the point is, let's assume the distance between the charges Q2 and Q3 from this point will be some distance of R3. So the potential will be the final potential minus initial potential. The initial potential is 0, so the final potential will be 1 by 4 pi epsilon naught. Since there are two charges, the potential will be due to two charges, Q1 by the distance is R2 plus Q2 by R3. The work done will for bringing a third charge equals Q3 times, or we can say work done equals Q3 by 4 pi epsilon naught Q1 plus Q2 by R2 by R3. This is the work done for bringing charge Q3, and for the total work done it will be total work done in arranging such a configuration is, we can sum the work done. W total equals W initial, the W for Q1 which is 0 plus W for Q2 plus W for Q3 which is W for Q2 which is 1 by 4 pi epsilon naught Q1 Q2 by R1 plus for Q3, this is this one, for Q3 it is Q3 by 4 pi epsilon naught times Q1 by R2 plus Q2 by R3. Now we can take 1 by 4 pi epsilon naught common here. 1 by 4 pi epsilon naught Q1 Q2 by R1 plus Q3 times Q1 R3 plus Q2 R2 by R2 R3 or we can write this as not like this, but we can multiply it individually. We can write it as Q3 Q1 by R2 plus Q3 Q2 by R3. So the total work done for arranging such a configuration is, these are the individual pairs along with their distances. The formula for how many pairs we need, like how many of this we will get, it is n times n minus 1 by 2 if we have 3 charges where n is the number of charges. In that case 3 times 3 minus 1 by 2, which is equals to 3 times 2 by 2. The final answer is 3 pairs. In case the number is 4, then we get 4 times 4 minus 1 by 2, 4 times 3 by 2, 1s are 2s are equals 6 pairs. And for where n is 2, 2 times 2 minus 1 by 2, it is 2 by 2 times 1, so only 1 pair. In such a case, the final answer for bringing a 2 charge system is 1 by 4 pi epsilon naught Q1 Q2 by R equals work done or potential energy. This is for 2 charge system. And the main formula for finding the number of pairs is n into n minus 1 by 2. I will be erasing this. Where this is and the formula for 3 charge system being this, the work done for bringing a 3 charge system. Basically that is what they wrote here. This is not the full formula, this is for bringing only Q3 charge. The total work done in assembling the charges at given locations is obtained by the work done in different steps. That is the final formula, which can be equal to the change in potential energy or the total work done. Potential energy of a system of 3 charges is given by equation, this equation. Given in the figure with the notation given in the figure. This is how the system looks. This is basically a 3 charge system, a 3 charge configuration. Again, because of the conservative nature of the electrostatic force, or equivalently the path independence of work done. Yes, the final expression for u, equation 2.26, this equation is independent of manner in which the configuration is assembled. No matter how the configuration, like maybe due to any force, gravity, any kind of force, this configuration was assembled, this equation will be true. The potential energy is characteristic of the present state configuration and not the way the state is achieved. Let's read the last statement again. The potential energy is a characteristic of present state of configuration and not the way the state is achieved. So no matter how the state is achieved, before statement they are repeating again, the potential energy is the characteristic of the present state, like how the present state is, but not the way how the state was achieved. It doesn't matter how you brought such a configuration. The question: four charges are arranged at the corners of a square ABCD of side D as shown in the figure 2.15. Find the work done required to put together this arrangement. B. A charge Q0 is brought to the center of the square, the four charges being fixed at its corners. How much extra work is needed to do this? Actually, if we need to solve such a question, pages. Now, a square, this is a square, and charges, let's first give the naming, A, B, C, D, plus Q, minus Q, minus Q, and plus Q. Plus Q, minus Q, HC is plus Q and minus Q, and minus Q. is the charge. The first question is, what is the work done in bringing such a system together? The number of pairs will be 6. And the distance is d. So the final formula will be u times u equals 1 by 4 epsilon naught. We can take d out because d is common, and we can write basically just the charges. First we can take A and B, AB plus, these are the charges. I will write the charges again. 8AB times AC times plus AD plus BC plus wait a second. AB BC plus, we can't take D common because this is a diagonal where this will be D root 2. Actually we can take D common, but sum will have a denominator of root 2. AB BC CD plus AD plus AC by D root 2 plus BD by root 2. In here U equals D1 by 1 by D 4 pi epsilon naught times AB is minus Q square, BC is also minus Q square, and CD is also minus Q square. AD as well is minus Q square plus AC and BD are Q square by root 2 plus Q square by root 2. This we can write it as Q we can take common, so it will be Q square we can take common and write it as Q square by D, KQ square by D minus 4 plus 2 by root 2. This we can write it as, we can rationalize this by 2 root 2 by 2, which is root 2. So the final work done will be 1 by 4 pi epsilon naught Q square by D root 2 minus 4. If you see here, the value is 1.4 minus 4. Then the value of U will be, delta U will be negative work done. So basically what we can interpret from this is U final is less than U initial. Yes, U final is less than U initial. The potential energy at U initial when they are at infinity is higher than the work done in bringing them is negative. Yeah. This is the first case and this is the total energy. Let's see the answer. Yes, this is the total work done. We got the correct answer. Now let's find this. Let's see the second question. A charge q naught is brought to the center E of the square. The four charges being held at fixed corners. How much extra work is needed to do this? So the second scenario, same square, plus q minus q plus q minus q plus q minus q plus q minus q. A, B, C, D. Now this is the center. They're asking if a test charge q naught is at infinity, then what is the work done to bring this charge from infinity to the center? We need to know this distance. If the whole distance from here to here is d root 2, then half of this distance from here to here will be d root 2 by 2, or we can write it as d by root 2 if we multiply the top with root 2. Now this we can write it as, now if you want to find the potential, the work done equals q times v, q naught times v, and the potential at center will be q naught times, the potential at center will be 1 by 4 pi epsilon naught. The potential at center will be individual charges, and we can take something out. I'll write this again. This is the equation we need to use, and W equals q naught times the 1 by potential at center will be 1 by 4 pi epsilon naught. We can take d as common, or not d but d per root 2. This we can take it as common. Now the charges will be q minus q plus q minus q. So the work done will be 0. The answer to the second question will be work done equals 0. Here I took, it should be by r by r by r, or by d root 2 by 2. That I took as common. So yes. And for another clarification, d root 2 by 2, if we rationalize it, we can write it as d times 2 by 2 root 2, which can be written as d by root 2. That is why here the d2 comes up. It's very useless in this question, but still. So let's see the solution. We got this solution to be correct, so I'll just read it. Since the work done depends on the final arrangement of the charges and not how they are put together, we calculate work done needed for one way of putting the charges at A, B, C and D. Suppose first the charge plus Q is brought to A, and then charges minus Q plus Q and minus Q are brought to B, C and D respectively. The total work needed can be calculated in steps. 1. Work needed to bring plus Q to A when no charge is present elsewhere. This will be 0. work done needed to bring minus q to b when plus q is at A. This is given by charge at B times the electrostatic potential at B due to charge plus q at A, which is q times V, which is equal to minus q times this equation. I am not reading the equation, I am only reading the steps. Work needed to bring charge plus q to C when plus q is at A and minus q is at B. This is given by charge at C times potential at C due to charges at A and B. The fourth step, work needed to bring minus q to D when plus q at A and minus q at B and plus q at C. This is given by charge at D times potential at D due to charges A, B and C. And add the work done in steps 1, 2, 3 and 4. The total work done required is minus q square by 4 pi epsilon d times 4 minus root 2, where the minus sign is taken outside and 4 minus root 2 is written inside the bracket. The work done depends only on the arrangement of charges and not how they are assembled. Any charge you can bring any time, the final answer will be same. By definition, this is the total electrostatic energy of the charges. Students may try calculating some work energy by taking charges in any other order they desire and convince themselves that the energy will remain the same. The extra work necessary to bring a charge Q0 to the point E when the four charges are at A, B and C. A, B, C, D is Q0 times electrostatic potential at E due to the charges at A, B and C, A, B, C and D. The electrostatic potential at E is clearly 0 since potential due to A and C is cancelled by that due to B and D. Plus Q minus Q0 plus Q minus Q0, so the total potential will be 0. 0 times Q will be 0, so the work done in bringing such a charge to the center of the square will be 0. No work is required to bring any charge to the point E. It might not be any test charge, it might be any big or small charge. The work done will always be 0. Now the next topic, potential energy in an external field. Potential energy of a single charge. Under the potential energy in an external field, the subtopic potential energy of a single charge. In section 2.7, the before section, we calculate the potential energy for 2 or the total energy of the system, the total potential energy of the system or the work done. The source of the electric field was specified, meaning they gave the potential, like where the electric field is originating from, which is the charges. The charges and their locations and the potential energy of the system of those charges was determined. It was given. In this section, we ask a related but distinct question. What is the potential energy of a charge Q in some given field? There is a field. If a charge is Q is placed at some point at the field, then what is the potential? We don't know the distance. We don't know the distance from the point that is originating this field. We don't know the amount of magnitude of the charge of the field. We don't know anything about that. We only know the electric field. This question was in fact the starting point that led us to the notion that electrostatic potential, but here we address this question again to clarify in what way it is different from the discussion in section 2.7. The main difference is that we are now concerned with the potential energy of a charge or charges in an external field. The external field E is not produced by given charges whose potential we wish to calculate. E is produced by sources external to given charges. The electric external sources may be known, but often they are unknown or unspecified. What is specified is that electric field E or the electrostatic potential V due to the external sources. We assume that the charge Q does not significantly affect the sources producing the external field, meaning if a Q charge is here, then another charge which is producing the charge is here. Due to this charge, it does not get displaced or does not affect the total electric field. We assume that this test charge Q0 does not affect the main charge. It might be due to some unspecified forces holding the main electric field producing charge, or it might be due to the Q naught being very minute compared to the main charge. This is true if Q is very small or the external sources are held fixed by other unspecified forces. Even if Q is finite, its influence on the external forces may still be ignored in situations where very strong sources far away at infinity produce a finite field E in the region of interest. Note again that we are interested in determining the potential energy of a given charge Q and later a system of charges in the external field. We are not interested in the potential energy of the sources producing the external electric field. The external electric field E and the corresponding external potential V may vary from point to point. By definition, V at a point P is the work done in bringing a unit positive charge from infinity to the point P. We continue to take potential at infinity to be 0. Thus, work done in bringing a charge Q from infinity to point P in external field is Q times V. This work is stored in the form of potential energy of Q. If the point P has position vector R to some origin, we can write potential energy of Q at R in an external field, which is QV, where VR is the external potential at point R. Thus, if an electron with a charge Q equals E, which is a standard electron charge, is accelerated by a potential difference of delta 1 volt, it would gain Q delta gain energy of 1.6 into 10 power minus 19 joule. This unit energy is defined as 1 electron volt or 1 eV. Basically, let's read the statement again. Work done in bringing a charge Q from infinity to point P, the external field is QV. The work is stored in the form of potential energy of Q. If the point P is position vector R related to some origin, we can write potential energy of Q at R in an external field. QV is R, where VR is the external potential at the point P. They provided the potential here, the potential difference due to some external electric field. Delta is given as 1 volt. Potential difference is 1 volt. So the work done can be calculated because Q times V Q times V delta V, this is provided as 1 volt. So the charge is QV. The work done in accelerating an electron through a potential difference of 1 volt is what we call 1 eV of energy. Basically, we are defining 1 eV of energy, which is 1.6 into 10 power minus 19 joules. The units based on EV are most commonly used in atomic, nuclear and particle physics. 1 kilo EV is accelerating 1000 electrons through a potential of 1 volt. The energy required, we can say that if it is 30 electron volts or 30 EV, we can say that the energy is the energy required to accelerate 30 electrons through a potential of 1 volt, at least to a potential difference of 1 volt, is equal to 30 EV. If we take as 1 kilo EV, we can take it as 10 power 3 EV, and the energy required to accelerate 1000 electrons through a potential of 1 potential difference of 1 volt, the energy, that energy is what we represent as 1 kilo electron volt, or maybe we can define it as in another way. The energy, this can be written as, it is just for understanding, 1 kilo EV we can define it as the energy required to accelerate 1000 electrons through a potential difference, or the energy gained by electrons when, it's not energy required but energy gained by electron when accelerated through a potential difference of 1 volt. This is for 1000 electrons. And if we want to define it for a single electron, 1 kilo electron volt for a single electron, then we can say the energy gained by a single electron by it getting accelerated due to a potential difference of 1000 volt, because this we can write it as E kV 10 power 3 volt. So the energy gained by an electron by going through or through a potential difference of 1000 volt. This is the amount of energy. Instead of joules, we use an electron volt. This unit based on EV are most commonly used in atomic, nuclear and particle physics, where 1 kilo electron volt equals 10 power 3 electron volts, which is equals to 1.6 into 10 power minus 16 joules. 1 mega electron volt equals 10 power 6 electron volt, which is goes on, and 1 giga electron volt, which is 10 power 9, which is in joules it is 1.6 into 10 power minus 10 joule, and 1 tera is 10 power 12 electron volt, which is still less than a joule. This has already been defined in page 117 of class 11 physics part 1 textbook. Potential energy, the next subtopic under potential energy due to an external electric field. This is the first case, where the first case was a single charge. For single charge, where they gave the potential here, the potential difference, an electron volt is getting accelerated, and this is the energy. And the next subtopic, potential energy of a system of two charges in an external field. This is for a single charge, which we took it as a single electron. Next, we ask, what is the potential energy of a system of two charges Q1 and Q2 located at R1 and R2 respectively in an external field? First, we calculate the work done in bringing charge Q1 from infinity to R1. Before, when it is not in an external field, this work done used to be 0, but here, as there is an external field here, the work done for sure will not be 0, and the work done will be Q times V, Q times not delta V, because it is brought from infinity. The initial potential will be 0, so it will be Q times potential. The work done will be Q times potential. The potential either be provided, or we defined a relation E equals V by L, or it is not completely correct. More specifically, it is minus delta V by delta L for two equipotential surfaces. Why? Because this is for a unit charge. Yes, this is the work done in bringing a single charge in from infinity to R1 in presence of some external field. The work done in this step is Q1 V R1. as I said here, Q times V, using equation 2.27, this equation. Next, we consider the work done in bringing Q2 to R2. In this step, work done is not only against the external field E, but also against the field due to Q1. Work done on Q2 against the external field. Work done on Q2 against the external field. The work done against Q2 on the external field will be the same equation like this: Q2 times VR2. Work done on Q2 against the field due to Q1, the electric field produced by the first charge. It will be the potential energy 1 by 4 pi epsilon naught Q1 Q2 by 4 pi epsilon naught by R, where R12 is the distance between Q1 and Q2. I have made use of equations 2.27 and 2.22. 2.22 equation is here, this equation. The potential energy of a two-particle system. By the superposition principle for fields, we add up the work done on Q2 against the two fields E and that due to Q1, work done in bringing Q2 to R2. We add up the work done on Q2 against the two fields E and we add the potential differences. The first one, this one being due to the external electric field, and this one due to being the charge which was there. Thus, the potential energy of the system, the total work done in assembling the configuration, is Q1 V1 R1. This is the potential and the energy or work done in bringing the first charge. This is the second charge for against the electric field. This is the second charge due to the first charge placed. Is there anything we can take common? No, there is nothing we can take common here, at least for all three of them. This is the final equation for assembling a two-particle system, that is against a external field. Two-particle system against an external field. Now, the next subtopic is potential energy of a dipole in an external field. So that we will see before let's see this example. Determine the electrostatic potential of energy of a system containing of two charges, 7 microcoulomb and -2 microcoulomb, and with no external field, placed at -9 centimeters, which is at the x-axis, -9 and 9 centimeter. Total distance is 18 centimeter. Determine the electrostatic potential energy of a system containing, this is with no external electric field. The direct formula 2.22. The direct formula is 1 by 4 pi epsilon naught Q1 Q2 by R. This formula if we use, where R is 18 centimeter, if we add up the two distances, 9 centimeter, 9 centimeter, then the 18 centimeter, we know the values of Q1 Q2, the constant, Coulomb's constant, 9 into 10 power 9, and 18 centimeter if we convert into meter by making it multiply with 10 power -2. Substituting values in this exact equation, we will get the answer. That is in case of no external field placed. Now, second question. How much work is required to separate the two charges infinitely away from each other? So they are asking work done to separate the charges infinitely away from each other. So let's assume we do not need to, I believe we do not need to move if there are two charges here. I think it is sufficient for us to move this charge to a position at infinity. So the Vf equals 0, so V initial equals the potential at that point. So the potential at that point will be 1 by 4 pi epsilon naught. If we are thinking of moving, let's assume we are moving 7 microcoulomb. We are moving 7 microcoulomb, which is 7 into 10 power minus 6 by 18 into 10 power minus 2. This is the potential. Wait, no. We are moving, if we take it like this is the initial potential. We are moving minus 2 coulomb charge. This is the final potential. I mean, this is the initial potential value, V initial. Then the work done equals V final minus V initial times Q. So V final minus initial will be minus 1 by 4 pi epsilon naught 7 into 10 power minus 6 by 18 into 10 power minus 2 times minus 2 into 10 power minus 6. This is the work done in bringing a charge. If we solve this, we will get a value of, let's solve it then, minus into minus plus, so 9 into 10 power 9 value of the Coulomb's constant times 7 into 10 power 4 by 18 times 2 times 10 power minus 6. This is 10 power minus 4. Then the value will be 1911, and denominator is completely cancelled. 7 is the only non-10 term. 7 into 10 power 9 times 10 power minus 4 times 10 power minus 6. 4 times 10 power minus 6. 7 into 10 power minus 1 equals 0.7 joule. This is the work done to separate the charges from infinitely far away from each other. I believe this is the answer. Let's check. Yes, 0.7 joule is negative. Okay, that is not the case. To bring them infinitely from each other, it is positive itself, yes. And the third question, suppose that the same system of charges is now placed in an external electric field E equals A times 1 by R square. A equals 9 into 10 power 5 Newton per Coulomb meter square. What will the electrostatic energy of the configuration be? Interaction of the two charges remains unchanged. In addition, there is an energy of attraction between the two charges. External field we find these are the potentials they are adding due to the external field. And the net electrostatic energy is This will be 0 minus 0.7. So 70 minus 20 minus 0.7 will be 49.3 joules. Potential. Okay, they gave it as A times 1 by R square, so we took it as 0.09 meter. A times 7 microcoulomb by 0.09 meter. This is the electric potential due to the external field. This both we added, and the total energy we also added. We will get the total energy here. And with this we solve the 3 questions. And the third subtopic is potential energy of a dipole in an external electric field, that I will solve after a 20 to 30-minute break. Let's continue. Potential energy. Potential energy of a dipole and external field. Consider a dipole with charges q1 equals plus q and q2 equals minus q and placed in a uniform electric field E as shown in figure 2.16. Potential energy of a dipole in a uniform electric field. The direction of the electric field is the right side. This is a dipole. Theta is the angle between the x-axis and the dipole. And 2a is the dipole length. P from negative to positive is the moment vector, dipole moment vector. Minus a cos theta and a cos theta being the cos component of the dipole length, half of the cos component of the dipole length. This much is a, so if we take a cos component of a, it will be a cos theta. Here the same way it is minus a cos theta because it is in different direction. Now let's continue reading, and this is along the x-axis. As seen in last chapter, in a uniform electric field, the dipole experiences no net force but experiences a torque tau given by tau equals p times E, where p is the vector, dipole moment vector, and E is electric field. This is cross product, meaning it can be written as p sin theta. Which will tend to rotate it unless P is parallel or anti-parallel to E. Suppose an external force torque external is applied in such a manner that just neutralizes this torque and rotates it in the plane of paper from angle theta 0 to theta 1 at an infinitesimal angular speed and without angular acceleration. The amount of work done by external torque will be given by W equals T external and delta d theta p sin theta d theta. Okay, so basically if this is in an electric dipole making an angle theta plus q and no, this is minus q and plus q, this is the electric field direction. Then let's read the textbook once more. Which will tend to rotate it unless P is parallel or anti-parallel to E. Suppose an external torque T is applied in such a manner that it neutralizes the torque and rotates it in a plane of paper from angle So in such a case, the dipole will have a torque in this direction due to the electric field. But for that torque, if we apply an equal and opposite torque, which is by external forces, this side and this side, which is this side and this side, this is tau external and this is tau electric field. And it is such a way that tau electric field is magnitude wise same as tau external. In such a case, the dipole will rotate from theta equals theta naught to theta equals a dipole will rotate from theta equals theta naught to theta equals theta 1 in a infinitely small speed, very small angular speed and angular acceleration omega, not omega, angular acceleration alpha will be 0. In such a case, the work done by applying that external torque and rotating this can be written as torque times d theta integrate equals work done this we know from the electric field, the first chapter, that tau equals Pe sin theta. The lower limit is theta naught to theta 1. So in tau place we can substitute the value. Here it is not theta naught but only theta. Here it is theta, and we know from the electric fields chapter that tau equals P sin theta. So the work done will be lower limit theta naught to upper limit theta 1 Pe sin theta with differentiating with respect to a small angle deflection theta, or we can just not cancel it, but we can say differentiation of work done will be total work done, and here dipole moment vector and electric field vector will be constant, so you can take them outside, and theta, so we will need to differentiate sin theta. Differentiation with respect to sin theta is minus cos theta So work done equals PE cos theta. I will exchange the limits to replace the negative sign. PE cos theta naught minus cos theta 1. We can write this as theta initial minus theta final as well. Work done equals P cos theta initial minus cos theta final. I believe this is the correct formula. This is for work done or potential energy change in a dipole. In an electric dipole. Yes, P cos theta initial minus cos theta final. This is the work done, or we can also say the change in potential energy. This work is stored as potential energy of the system. We can then associate potential energy u theta with an inclination theta of the dipole similar to the other potential energies. There is a freedom in choosing the angle where the potential energy u is taken to be 0. We can take one of the potential energies to be 0. A natural choice is to take theta equals pi by 2. An explanation for it is provided towards the end of the discussion. We can then write the potential energy change is equal to P cos pi by 2, which is cos 90 degree, which is 0. So P cos theta is, this will be negative P cos theta, which we can write as minus P dot E, which is a scalar product. This expression can alternately be understood from equation 2.29, which is this equation. How you can understand that? Wait, this section. Yes, actually this 2.29 equation is a two particle system in an external field. Here as well, in a dipole in an electric field, it's exactly the same two particle or two charge system in an external field. The change is that the charges are opposite in nature. And if we apply the same here, potential energy expression then reads u theta equals q times VR1 minus VR2. Here minus is because the charges is opposite. One is a positive and one is a negative charge. Minus q square, because plus q times minus q equals minus q square, by 4 pi epsilon naught times 2a. 2a is the dipole length or the distance between the two charges. Here R1 and R2 denote the position vectors of plus q and minus q. Now the potential difference between positions R1 and R2 equals the work done in bringing a unit positive charge against field from R2 to R1. The displacement parallel to the force is 2a cos theta. Thus, here R1 and R2 denote the position vectors of plus q and minus q. Now the potential difference between positions R1 and R2 equals the work done in bringing a unit positive charge against field from R2 to R1. The displacement parallel to the force is 2a cos theta. Thus VR1 minus VR2 equals minus E times 2a cos theta. We thus obtain, let's read the statement again. R1, R2 denote the position vectors of plus q and minus q. Now the potential difference between positions R1 and R2 equals the work done in bringing a unit positive charge against field from R2 to R1. The displacement, basically they are using the formula that W equals Q delta V, and for a unit positive charge this is 1, W equals delta V, and in that case the difference between potential is indeed the work done, where we bring the charge against the electric field from R2 to R1. Why we are bringing the charge against electric field is, if we brought it, then only it will be positive. If we brought it with respect to the with side of the electric field, then the work done will be negative if direction of action is same as electric field. But we need positive, so we consider it against the electric field, so this is not considered. That doesn't mean it is wrong, just not considered, because we will get an opposite value. And work done and I think they used another formula of V equals delta V equals E times delta L, or more specifically minus E delta L. So they got delta V equals minus E to A cos theta. In this equation we thus obtain potential energy equals minus P cos theta minus Q square by 4 pi epsilon naught times 2A, which is minus P dot E minus Q square by 4 pi epsilon naught by 2A. We note that U dash differs from U by a quantity which is just a constant for a given dipole. Q square by 4 pi epsilon naught, where Q square is a charge, 4 pi epsilon naught, 1 by 4 pi epsilon naught is Coulomb's constant, and 2A is the dipole length. What is here? U theta equals this is when we move, or the change in potential energy of the dipole as this dipole rotates with very small and constant speed and zero acceleration. This is the change in potential when that happens, and this is in an electric field. But in case of when we take the two particle system, in case of with presence of electric field, we will see this differs by a quantity which is constant for a given dipole. Since a constant is insignificant for potential energy, we can drop the second term in equation 2.34 and reduces to equation 3.2. Since we are finding the potential difference, even if it is any kind of constant, as we saw in a before page, in case of Let's avoid it anyways. Let's just say that when we are finding difference, a constant variation or a variation with like with a constant doesn't matter, because thirty minus 20 is 10. In case of potential difference, it is 10 volt, and we take another value of 40 minus 30, or 400 minus 390. This is also 10. Because of such a reason, we do not consider constants in case of difference, and when we neglect or reduce this quantity to 0, we will get the final answer, the potential difference, to be equal to what we got here. These are just two cases where we are finding potential energy, difference in potential energy. We can now understand why we took theta naught equals pi by 2. In this case, the work done against the external field E in bringing plus Q and minus Q are equal and opposite. Basically, they are saying about the equatorial plane where potential is 0. Now understand why we took theta naught. In this case, the work done against that external field E in bringing are equal and opposite and cancel out, that is 0. That is why we took theta to be 90 degrees. Let's see an example. A molecule of a substance has a permanent electric dipole moment of magnitude 10 power minus 29 coulomb meter. A mole of this substance is polarized at low temperature by applying a strong electrostatic field of magnitude 10 power 6 volt per meter. The direction of the field is suddenly changed by an angle of 60 degree. Estimate the heat released by a substance in aligning its dipoles along the new direction of the field. For simplicity, assume 100% polarization of the sample. Let's try to solve the question. They're basically asking the change in potential energy. Let's start in a new page. A substance, let's assume they took it in a beaker. This substance is has a permanent electric dipole, meaning its molecules are plus minus plus minus plus minus plus minus and so on. When we apply electric field to this, let's assume we are applying a strong electric field, plus 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 minus minus minus, and when we apply such a thing, such a strong electric field in this direction, the molecules will be polarized, meaning This is what we call as polarization, and they gave the value of electric field to be dipole moment magnitude is P is 10 power minus 29 coulomb meter. This is not centimeter but coulomb meter. Power 6 volt per meter. Direction of the field is suddenly changed by an angle of direction of the field is suddenly changed by an angle of 60 degree. Estimate the heat released by a substance and aligning its poles in the new direction of the field. For simplicity, assume 100% polarization of the sample. And they gave the quantity to be N equals number of molecules equals 1 mole equals 6 into 10 power 23 molecules. So when we change the electric field again by pi by 3, we can write 60 degree as pi by 3 radians as well, 60 degree. Then for a single molecule, the change in potential will be delta U equals PE cos theta the formula was P cos theta initial minus cos theta final. So delta U should be, for single molecule, PE cos 0 minus cos 60 degree. It will be PE cos 0 is 1, cos 60 is 1 by 2. So PE by 1 by 2 times 6 into 10 power 23 will give us the total change in potential energy or the heat released. It will be equal to PA is they gave as 10 power minus 29 coulomb per meter. Yes, minus 29 coulomb per meter. Electric field is 10 power 6 volt per meter by 2 times 6 times 10 power 23. Ones are 3s are 10 power 23 plus 10 power 6 is 10 power 29. 10 power 29 times 10 power minus 29 cancel, and the final change in potential energy is 3 joule. I believe this is the correct answer. So yes, the change in potential energy is 3 joule. As for how they did it, here dipole moment of each molecule is 10 power minus 29 coulomb meter, as 1 mole of substance contains 6 into 10 power 23 molecules. Total dipole moment of all molecules P equals 6 into 10 power 23 times 10 power minus 29 equals 6 into 10 power minus 6. As such, U equals minus PE cos theta minus 6 into 10 power 6 times 10 power 6 cos 0 equals minus 6 joule, and cos 60, if we apply, it will be 1 by 2, so it will be minus 3 joule. Change in potential is minus 3 minus of minus 6 joule, so it will be 3 joule. So the loss in potential energy, this must be the energy released by a substance in form of heat in aligning its dipoles. Electrostatics of conductors, the next topic. More pages to go. Now let's start with the topic, electrostatics of conductors. Conductors and insulators were described briefly in chapter 1. Conductors contain mobile charge carriers, mobile meaning movable charge carriers. In metallic conductors, these charge carriers are electron in a metal. The outer valence electrons part away from their atoms and are free to move. These electrons are free within the metal but not free to leave the metal. Conductors and insulators were described briefly in chapter 1. Conductors contain mobile charge carriers in metallic conductors. These charge carriers are electron in a metal. The outer valence electrons part away from their atoms and are free to move. These electrons free within the metal but not free to leave metal. The electrons are able to leave, move within the metal, but they won't be able to leave the metal. The free electrons form a kind of gas. They collide with each other and with the ions and move randomly in different directions. An external electric field, they drift against the direction of the field. The positive ions made up of the nuclei and the bound electrons remain held in their fixed position. In an electrolytic conductor, the charge carriers are both positive and negative ions, but the situation in this case is more involved. The movement of the charge carriers is affected by both the external electric field as also by the so-called chemical forces, which can be attraction forces, repulsion forces, etc. We shall restrict our discussion to metallic solid conductors. Let us note important results regarding electrostatics of conductors. We will be restricting our topics to metallic solid conductors. Inside a conductor, electrostatic field is 0. Main points regarding electrostatics of conductors. inside a conductor, electrostatic field is 0. Consider a conductor neutral or charged. There may be an external electrostatic field in the static situation when there is no current inside or on the surface of the conductor. The electric field is 0 everywhere inside the conductor. Consider a conductor neutral or charged. There may also be an external electrostatic field in this static situation, and there is no current inside or on the surface of the conductor. The electric field is 0 everywhere inside the conductor. Condition 1: no current inside or on surface of conductor. Then the electric field inside a conductor will be 0. This fact can be taken as a defining property of a conductor. A conductor has free electrons. As long as the electric field is not 0, the free charge carriers would experience force and drift. In the static situation, the free charges have so distributed themselves that the electric field is 0 everywhere inside. Final point: electrostatic field is 0 inside a conductor. Let's read again. This fact can be taken as the defining property of a conductor. A conductor has free electrons. As long as the electric field is not 0, the free charge carriers would experience force and drift. In the static situation, the free charges have so distributed themselves that the electric field is 0 everywhere inside. If there is electric field, the charge carriers, meaning electron, will move, but in rest situation the free charges have distributed, they have so much distance between them that electric field is 0 everywhere inside. Electric field is 0 inside a conductor. Okay, fine. Basically they are saying a reason that the free charges have distributed themselves so much that the electric field will be 0 inside the conductor. The one thing that needs to be remembered is that inside a conductor the electric field is 0. At the surface of a charged conductor, electrostatic field must be normal to the surface at every point. This point we saw before. At the surface of a in equipotential surfaces, at the surface of a charged conductor, electrostatic field must be normal to the surface at every point. If E were not normal to the surface, it would have some non-zero component along the surface. Free charges on the surface of the conductor would then experience force and move. In the static situation, therefore, E should have no tangential component. Thus, electrostatic field at the surface of a charged conductor must be normal to the surface at every point. For a conductor without any surface charge density, field is 0 even at the surface. If charge is 0, the field is 0. Basically, this is the exact same definition as to why the electric field should be normal. This came in the electric potential topic before in this chapter itself. If there was a non-zero component, which might be sine theta or cos theta component, if it is acting on the surface, then charges should move. This will create electricity, but that does not happen. The interior of a conductor can have the first 2 points we learned is, the first point is that the electric field inside a conductor is always zero, because the free charges have distributed themselves so much that the electric field inside will be zero, and the condition that there should be no current flowing on either inside or the surface of the conductor. The interior of a conductor can have, and the second point is the electric field must always be perpendicular to the surface. The interior of a conductor can have no excess charge in the static situation. Interior of a conductor can have no excess charge in the static situation. A neutral conductor has equal amounts of positive and negative charges in every small volume of this surface element. When the conductor is charged, the excess charge can reside only on the surface in the static situation. A neutral conductor has equal amounts of positive and negative charges in every small volume or surface element. When the conductor is charged, the excess charge can reside only on the surface in the static situation. The excess charge can reside only. A charged conductor can only store its charge on the surface in static situation. This follows from the Gauss law. Consider any arbitrary volume element V inside a conductor. On the closed surface S bounding the volume element V, electrostatic field is zero. Thus, the total electric flux through S is zero. Hence, by Gauss law, there is no net charge enclosed by S. But the surface can be made as small as you like, that is, the volume V can be made vanishingly small. This means there is no net charge at any point inside the conductor, and any excess charge must reside at the surface. Basically, they are saying there will be no charge inside the conductor. There will only be charge on the conductor, because even if we take a charge, let's read just one more. When the conductor is charged, the excess charge can reside only on the surface in a static situation. This follows from Gauss law. Consider any arbitrary volume element V inside a conductor. On the closed surface S bounding the volume element V, electrostatic field is zero. Thus, the total electric flux through S is zero. Hence, by Gauss law, there is no net charge enclosed by S, but the surface S can be made as small as you like. The volume can be made vanishingly small. This means there is no net charge at any point inside the conductor. Gauss law basically is for calculating electric flux. If you take a conductor, let's assume this is a spherical shell, this is a volume V. We know that the electric field on the surface is zero. The surface element is zero. E surface is zero. As we learned before, the electric field is always perpendicular to the surface, meaning there is no surface component. If there was, the charges would be moving. In such a case, E surface is zero. Then the total flux, if the electric flux phi is defined as the number of electric field lines passing through a surface. when electric field itself is 0, Gauss law stating that phi equals Q enclosed by epsilon naught. If this becomes 0, this will also become 0, as epsilon naught is a constant value, which is the permittivity of free space, which is constant as 8 point something into 10 power minus 12. So Q enclosed, meaning the charge inside this volume will be 0. This proves that the there will be no charge inside the conductor. There won't be any electric field inside the conductor because the free electrons on the surface are distributed very much, and the electric field lines are always perpendicular to the surface. The third point, there is no charge enclosed inside the surface, in the volume inside. Let's see the fourth point. Electrostatic potential is constant throughout the volume of the conductor and has the same value as inside on its surface. This is also a point which I told before. Basically, if this is a spherical conductor, or I mean a spherical shell, then the electric field inside will be 0 and charge will be 0, but potential will not be equal to 0. Potential inside is equal to the potential on the surface. This is for a spherical object. This follows from results 1 and 2 above. Since electric field is 0 inside the conductor and has no tangential component on the surface, no work is done in moving a small test charge with the conductor and on its surface. That is, there is no potential difference between any 2 points inside or on the surface of the conductor. Hence, the result, if the conductor is charged, electric field is normal to the surface. This means the potential will be different for a surface and a point just outside the surface. In a system of conductors of arbitrary size, shape and charge configuration, each conductor is characterized by a constant value of potential. But this constant may differ one conductor to the conductor. Since electric field is 0 and charge inside is 0, and there is no work done in moving a charge inside the conductor, that is, there is no potential difference. The potential inside is completely constant, so there is no work done, meaning no potential difference inside or on the surface of the conductor. This we call it as equipotential surfaces. Hence the result, if the conductor is charged, electric field normal to the surface exists, perpendicular to the surface exists. This means potential will be different for the surface. Potential will be different for the surface. Yes. Potential will be different on the surface and a point outside the surface or above the surface. In a system of conductors of arbitrary size, shape and charge configuration, many shapes, different size, different charge configuration, each conductor is characterized by a constant value of potential, but this constant may differ from one conductor to other conductor. The fifth point, they mentioned electrostatic field at surface of a charged conductor must be normal to the surface at every point. For a conductor without any surface charge density, meaning charge is 0, field is also 0. Even at the surface, they gave C result 5. electric field at the surface of a charged conductor. E equals sigma epsilon naught, where sigma equals Q by A, charge per area, is the surface charge density, and and epsilon naught is the permittivity of free space, and n cap is a unit vector normal to the surface, in the outward direction. To derive the result, this is the electric field Q by A times, this might be the total electric field, to derive the result, choose a short cylinder as the Gaussian surface about any point P on the surface. This is the figure. Let's see the figure first. The Gaussian surface, which is like a pillbox, chosen to derive equation 2.35 for electric field at the surface of a charged conductor. Here, since the total charge is unequal for the surface of a conductor and we can't take the whole surface of a conductor, instead of that we took charge density sigma, and this is the pillbox shaped short cylinder, surface charge density, and delta S is a small area, and E is the electric field. The pillbox is partly inside and partly outside the surface of the conductor. It has a small area of cross section delta S and negligible height. Just inside the surface, the electrostatic field is 0. Just outside the field is normal to the surface with magnitude E. Thus, the contribution to the total flux through the pillbox comes only from the outside circular cross section of the pillbox. This equals to plus or minus E delta S. Flux equals Q by epsilon naught. This is another formula for electric flux. When charge density is greater than 0 and negative for charge density is lesser than 0. Since overall a small area delta S, E may be considered constant, and E and delta S are parallel or anti-parallel. The charge enclosed by the pillbox is sigma delta S. By Gauss law, E delta S equals sigma delta S by epsilon naught. So E equals magnitude of sigma by epsilon naught. Including the fact that electric field is normal to the surface, we get the vector relation is true for both signs, sigma for greater or lesser than 0. Basically, they took a surface, they took a cylindrical structure, here. This has a surface area of a small surface area of delta S and negligible height. Electric field is pointing outwards. In such a case, the flux will be E times the electric field times delta S. I believe it will be, the area vector is parallel or anti-parallel to the electric field. So cos theta, so theta, if the both are parallel or anti-parallel, can either be 0 degrees or 180 degrees, meaning phi can be plus or minus E epsilon naught, E delta S. This is one value of the phi, and when we take this pillbox shaped or cylindrical structure as a Gaussian surface, we will get phi equals q by epsilon naught, but instead of taking q, we can take it as surface charge density by epsilon naught times delta S. Now how we got sigma delta S equal to charge is because charge density is q by A. This area is, we can write area equal to delta S, so q by delta S times delta S, sigma times delta S cancel, sigma times delta S equals q. This is how we got sigma delta S by epsilon naught equals phi, which is the electric flux. Now equation 2, equation 1, both LHS equal, so equate RHS. In such a case, E delta S equals sigma delta S by epsilon naught. Now delta S cancel, E equals magnitude of sigma, where sigma is a charge density, by epsilon naught. We will get this derivation or relation. This is the fifth property, saying that electric field at the surface of a charged conductor, and one more, here it is n cap, because the electric field is normal to the surface, and this electric field we found out is the electric field at the surface of I believe a charged conductor. Yes, a charged conductor. Okay, let's continue reading. the next topic, let's revise what we read. The first topic is about the electric field being zero inside the conductor because the free charges are spread or distributed, which will cause the electric field to be zero. And next, there is no charge inside the conductor. This we can prove through the Gaussian law. And next property being electric field is always normal to the surface. And the fourth property is electric potential inside a surface is same as the on the surface, because the work done in moving a charge inside a surface will be zero, because the potential will be constant and the potential difference will be zero. And the next property, electrostatic shielding. Consider a conductor with a cavity with no charges inside the cavity. A remarkable result is that the electric field inside the cavity is zero, whatever be the size and shape of the cavity, and whatever be the charge on the conductor and the external fields in which it might be placed. We have proved a simple case of its result already. The electric field inside a charged spherical shell is zero. The proof of the result for the shell makes use of the spherical symmetry of the shell, see chapter 1. But the vanishing of the electric field in the charge-free cavity of a conductor is, as mentioned above, a very general result. A related result is that even if the conductor is, let's see the diagram first. The electric field inside a cavity of any conductor is zero. All charges reside only on the outer surface of the conductor within the cavity. There are no charges placed in the cavity. Basically, all these rules seem to be the same thing, stretching again and again, but it might be useful and they are explaining other topics. Or maybe the importance of this. The electric field inside a cavity of any conductor is zero. All charges inside reside only on the outer surface of a conductor with cavity. There are no charges placed in the cavity. E is zero, charge density is zero, V is V surface. Constant electric field conducting body. Now let's go. Is charged or charges are induced on a neutral conductor by an external field. All charges reside only on the outer surface of a conductor with cavity. The proofs of the result noted in figure 2.18 are omitted here, but we note their important implication. Whatever be the charge and the field configuration outside, any cavity in a conductor remains shielded from outside electric field influence. The field inside the cavity is always zero. This is known as electrostatic shielding. This effect can be made use of in protecting sensitive instruments from outside electrical influence. Figure 2.19 gives a summary of the important electrostatic properties of a conductor. Let's read the sixth property once more. Basically, electrostatic shielding is the unaffectedness of the cavity from any other electric field influence from outside the conductor, even if the conductor is charged or uncharged. Consider a conductor with a cavity with no charges inside the cavity. A remarkable result is that the electric field inside the cavity is zero. Whatever be the size and shape of the cavity, and whatever be the charge on the conductor and the external field in which it might be placed, we have proved a simple case of this result already. The electric field inside charged spherical shell is zero. The proof of the result for the shell makes use of the spherical symmetry of the shell, but the vanishing of electric field in the charge-free cavity of a conductor is mentioned above a very general result. In related result is that even if the conductor is charged or charges are induced on a neutral conductor by an external electric field, all charges reside only on the outer surface of a conductor with cavity. The proofs here are omitted, but we note their important implication. Whatever the charge and field configuration outside, any cavity in a conductor remains shielded from outside electric influence. The field inside the cavity is always and will be zero. This is known as not only the field but even the charge density will also be zero. This is known as electrostatic shielding. The effect can be made use of in protecting sensitive instruments from outside electrical influence. This is the figure 2.9. Some of the important electrostatic properties of a conductor. This is the electric field formula we derived, where the electrostatic field, the electric field, which is equal to sigma by epsilon naught times the n vector. This is on the surface, where here charge seems to be induced, and potential here is representing, the first figure represents how the electric field and charge density rho are zero. Here it represents how the electric field on the surface is equal to sigma by epsilon naught times n cap. Here it represents how the potential inside the conductor will always be equal to the potential on the conductor, on the surface of the conductor. And the fourth property being, a cavity inside the conductor will also have electric potential and charge density to be zero. Example 2.7, I will not highlight it, but a comb run through one's dry hair attracts small bits of paper. Why? What happens if the hair is wet or if it is a rainy day? Remember, a paper does not conduct electricity. Question 2. Ordinary rubber is an insulator, but special rubber tires of aircraft are made slightly conducting. Why is this necessary? Vehicles carrying inflammable materials, meaning they can be flammable, they can easily catch fire, usually have metallic ropes touching the ground during motion. Why? A bird perches on a bare high power line and nothing happens to the bird. A man standing on the ground touches the same line and gets a fatal shock. Why? Let's see the solution to the first question. This is because the comb gets charged by friction. If you see in the first chapter, there are three methods of charging. The first is by friction, the second is by conduction, the third is by induction. This is because the charge gets the comb gets charged by friction, the molecules in the paper get polarized by the charged comb, resulting in a net force of attraction. If the hair is wet or if it is a rainy day, friction between hair and comb reduces, the comb does not get charged, and thus it will not attract small bits of paper. When you run a comb through your hair, when you do that, the comb will lose electrons. When you do that by friction, the comb will lose electrons, and as it loses electrons, the comb will get a positive charge. If it gets a positive charge, it will give electric field. Under this electric field, thin bits of paper will get polarized, meaning the dipole inside will be minus plus, minus plus, and minus plus. Because of this polarization, they will be attracted. This is why paper will attach to the comb. That is basically what they say. But when it is wet, your hair is wet, the friction is reduced and the loss of electron is also reduced, and the polarization power, if there is less charge on the comb, the polarization power is also reduced, and there is less attraction. Even if they might get attracted, there is a less power here. Or during a rainy day, there is high moisture content, so friction is reduced. Yes, the second question, ordinary rubber is an insulator, but special rubber tires of aircraft are slightly made conducting. Why is this necessary? Let's see the solution to the second question. To enable them to conduct charge produced by friction to the ground, as too much of static electricity accumulated may result in spark and result in fire. This is the introduction. These are introduction to the next topic, actually, dielectrics and polarization. The same reason when tires are moving in the ground or rolling in the ground, they either lose or gain electrons, which will induce a charge. This charge, if it is accumulated too much, it could potentially cause a spark, which will lead to a fire. Does that look like a fire? This fire, if there is a fire, airplane danger, if inflammable part material catches fire, then explosion. Because of that, if the tires are made to be conductive, they will send the charge back to the earth, and in case of the container containing flammable material, the charges touching the ground will send back the electricity back to the earth. In such a case, the charge accumulation would be reduced. And the third reason, the fourth question, a bird perches on a bare high power lane, bare meaning non-insulated or directly on a direct line, and nothing happens to a bird. Man standing on a ground touches the same line and gets a fatal shock. Why? Bird, even if there is no way to pass the electricity, but a man on the ground, if it touches, the electricity will pass through the man and go into the ground. This will form a circuit. This will lead to current passes only when there is difference in potential. Basically, we can understand that when there is a high power line, let's assume this is a high power line. This is a lightning symbol, and if a bird sits on this line, there is no potential. The potential across these 2 points, across these 2 terminals, will be same. Actually, that is not true, but let's just say the current cannot pass through the bird because there is no potential difference. The potential will be same. Because of that, nothing will happen to the bird. But when a man touches this line, then because he is standing on earth, which has zero potential, a low potential, the current from here having a potential V, earth will have always a potential of 0. It can either provide electrons or take electrons, so charges flowing will flow from man to the earth. This is very dangerous to the man. That is why I said current passes only when there is difference in potential. If you ask, is that why people wear rubber slippers to avoid electricity? That might be the case, to avoid contact with the earth. These are the reason questions. Now let's go to the next main topic, dielectrics and polarization. Dielectrics are non-conducting substances. In contrast to conductors, they have no or negligible number of charge carriers. Recall from section 2.9 what happens when a conductor is placed in an external electric field. When a conductor is placed in an external electric field, the charges will experience a drift and current is formed. The free charge carriers move and charge distribution of the conductor adjusts itself in such a way that the electric field due to induced charges opposes the electric field within the conductor. This is given in 2.9. Dielectrics and polarization. Dielectrics are non-conducting substances. In contrast to conductors, they have no or negligible number of charge carriers. Recall from section 2.9 what happens when a conductor is placed in an external electric field. The free charge carriers move and charge distribution in the conductor adjusts itself in such a way that electric field due to induced charges oppose the external field within the conductor, like this. In a conductor in an electric field, the electrons will be accumulated at one side. Okay, just a minute. Dielectrics and polarization. Dielectrics are non-conducting substances. In contrast to conductors, they have no or negligible number of charge carriers, which is electrons. When a conductor is placed in an electric field, the free charge carriers, electrons, will be accumulated in one side. In this case, when the electric field is this side, the negative charges, which is electrons, got accumulated on this side, and the positive charges, which is actually not the positive charges moving, but due to the lack of negative charges, positive charge is created in this place. In such a case, there is a internal magnetic field. This magnetic field, as the magnetic field, the electric field will always be from positive to negative direction. Because of that, this electric field will be in this direction. And when we add the total electric field of E outside plus E inside, it will be 0. This is in case of a conductor. Difference in behavior of a conductor and a dielectric in an external electric field. Here it seems that not all the charges are accumulated on the left side, and the charge difference created inside seem to be less. In such a case, the internal electric field seems to be not equal to the external electric field. So the total sum of the electric field will not be 0. The free charge carriers move, and charge distribution in the conductor adjusts itself in such a way that the electric field, due to induced charges, opposes the external field within the conductor, which is the opposing electric field E inside. This happens until in the static situation the two fields cancel each other and the net electric field in the conductor is 0. In dielectric, this free movement of charge is not possible. It turns out that the external field induces dipole moment by stretching or reorienting molecules of the dielectric. The collective effect of all the molecular dipole moments in net charges on the surfaces of the dielectric will produce a field that opposes the electric field. The collective effect for all the molecular dipole moments is net charge on the surface of the dielectric, which produces a field that opposes the external field. The collective effect of all the molecular dipole moments on the surface, which produce a field that opposes the external field. Is the net charges on the surface of the dielectric. Unlike in a conductor, however, the opposing field is so induced does not exactly cancel the electric field, it only reduces it. The extent of the effect depends on the nature of the dielectric. To understand the effect, we need to look at a charge distribution of a dielectric at molecular level. Let's read the paragraph again. Turns out the external field induced dipole moment by stretching or reorienting molecules of the dielectric. The collective effect of all the molecular dipole moments is net charges on the surface of the dielectric, which produce a field that opposes the electric field, basically saying the same thing. And basically, instead of this free movement of charges, they're saying the dipole moment is by stretching the molecules or reorienting the molecules of the dielectric. The collective effect of all the molecular dipole moments is net charges on the surface of the reactor which produce a field that opposes the electric field, and this is less than the outside external electric field and doesn't cancel the electric field, it only reduces it. The extent of the effect depends on the nature of the dielectric material. To understand the effect, we need to look at the charge distribution of a dielectric at the molecular level. Some examples of polar and non-polar molecules. H and H, it is a polar molecule because hydrogens, both are hydrogens, and the electronegativity the hydrogen is already a less electronegative molecule, and because both are hydrogens, it is a non-polar molecule. There is no partial charge created, or so there is no dipole moment. And as for CO2 as well, it is a non-polar molecule because if we see O, CO, here the direction dipole moment, here also dipole moment, and this both cancel out and the total dipole will be zero, net dipole moment will be zero. But in case of HCl, that is not the case. As HCl is extremely electronegative, it will pull all the electrons together to its side. Because of that, the Cl molecule, Cl atom will gain a negative charge, a partial negative charge, whereas H will gain a positive charge. This is a net moment. And here, wait, but they showed it this side, I'm not completely sure. Wait, yes, as we saw before in a dipole, the dipole moment vector is always from negative to positive. Because of that reason, they pointed the vector towards that side. And in case of a H2O molecule, due to H2O possessing lone pair of electron, the shape is bent shape, where this is the shape, and oxygen is electronegative and it will pull all the electrons, and the net dipole moment will be this side, this being the p vector from positive to negative. The molecules of a substance may be polar or non-polar. In a non-polar molecule, the centers of a positive and negative charges coincide. The centers of the positive and negative charges coincide. The molecule that has no permanent or intrinsic dipole moment, examples like we can say that a non-polar molecule, the centers of positive and negative coincide, meaning it's not exactly like this, it will be more like, in such a case there is no polarization here, as because they are coinciding. And this way I can say these kind of molecules do not have a permanent dipole. These are the non-polar molecules. We can define them as molecules that do not have a permanent or an intrinsic dipole, which is nothing but positive and negative charge separation. Examples of non-polar molecules are oxygen, where both are oxygen molecules, so electronegativity will be same, and hydrogen, H2, here in this case, molecules which because of their symmetry have no dipole moment. On the other hand, a polar molecule is one in which the centers of positive and negative charges are separated even when there is no external field. Such molecules have a permanent dipole moment. An ionic molecule such as HCl or a molecule of water are examples of polar molecules. Let's see the diagram first. A dielectric develops a net dipole moment in an external electric field. A. Non-polar molecules. B. Polar molecules. This is in an external electric field. Here there is no external electric field. They are concentric here. In case of non-polar molecules, in case of electric field, they separate like this. And in case of polar molecules here, they are arranged like this. And when there is an external electric field, they arrange in all, if you see here, all the minus is in one direction and the plus are in one more direction. In an external electric field, the positive and negative charges of a non-polar molecule in an external electric field, the positive and negative charges of a non-polar molecule are displaced into opposite directions like this. The displacement stops when the external force on the constituent charges of the molecule is balanced by the restoring force due to internal fields of the molecule in the molecule. Stops when the external force on the constituent charges of the molecule is balanced by the restoring force due to internal fields in the molecule. The non-polar molecule thus develops an induced dipole moment. The dielectric is said to be polarized by the external field. When the non-polar molecule develops an induced dipole moment, we consider that the dielectric is polarized by the external field. We consider only the simple situation when the induced dipole moment is in the direction of the field and is proportional to the field strength. Simple situation when the induced dipole moment is in the direction of the field. Simple situation where induced dipole is in the direction of the field and is proportional to the field strength. As the field strength increases, dipole strength also increases. The dipole is in this direction from negative to positive, and positive to positive side, negative should be there. So electric field is also in this direction. As the electric field strength increases, the separation also increases. So we can say that the dipole moment in the direction in the field and is proportional to the field strength. As the field strength increases, the dipole moment also increases. Substances for this assumption is true are called linear isotropic dielectrics. Linear isotropic dielectrics are substances which we can say that as the dipole moment, as the external electric field increases, the dipole moment also increases. Linear isotropic dielectrics. dielectrics where the external field is proportional to dipole moment. The included dipole moments or different molecules add up, giving a net dipole moment of the dielectric in the presence of the external field. The induced dipole moments of different molecules add up the induced dipole moments of different molecules add up, giving a net dipole moment of the dielectric in the presence of the external field. We saw somewhere the individual dipole, if they gave 1 mole if they gave the dipole moment P for a single molecule, P they gave for a single molecule. For finding the total dipole moment, we multiplied, they gave for a single molecule, total number of molecules is 1 mole. So we multiplied this single dipole moment of a single molecule times Avogadro's number, which is 6 into 10 power 23. This will get the total dipole moment or net dipole moment of all the molecules. That is what they are saying here. Basically, adding up all the individual dipole moments, you will get the total dipole moment of the entire dielectric. In the presence of an external field. Dielectric with polar molecules also develops a net dipole moment in an external field, but for different reason. In the absence of any external field, the different permanent dipoles are oriented randomly due to thermal agitation, so the total dipole moment is 0. For a polar molecule, for a single molecule, there will be dipole moment. But P net will be 0 because due to thermal agitation, they will be arranged in various directions, plus minus minus plus plus minus minus plus plus minus. In such a case, the total dipole moment will be 0. When an external field is applied, the individual dipole molecules tend to align with the field. When summed overall, the molecule, there is then a net dipole moment in the direction of the external field. That is, dielectric is polarized. When we see a net dipole moment in the direction of the electric field, that is to say that the dielectric is polarized. The extent of polarization depends on the relative strength of two mutually opposite factors. The dipole potential energy, the external field tend to align the dipoles with the field, and thermal energy tending to disrupt the alignment. Let's see that again. The extent of polarization depends on the relative strength of two mutually opposite factors. The dipole potential energy in the external field tending to align the dipoles with the field, and thermal energy tending to disrupt the alignment. Thermal energy will try to disrupt the alignment, but the potential energy will try to maintain the alignment. There may be, in addition, the induced dipole moment effect as for non-polar molecules, but generally the alignment effect is more important for polar molecules. Thus, in either case, whether polar or non-polar, a dielectric develops a net dipole moment in the presence of an external field. The dipole moment per unit volume is called polarization and is denoted by capital P for linear isotropic dielectrics. So they are saying capital P is the dipole moment per unit volume equals capital P. This is equal to epsilon naught chi e times E. This is a formula, I'm not sure how they derived it, but where chi E is a constant characteristic where we saw electric field is directly proportional to dipole moment. Dipole moment is directly proportional to electric field. As electric field increases, net dipole moment also increases. It is given here. So maybe this is a constant added where epsilon naught and chi e are constant added with the proportionality, and dividing this per unit volume we will get this maybe, where chi is a constant characteristic of dielectric and is known as electric susceptibility of the dielectric medium. It is known as chi e is known as electric susceptibility of the dielectric medium. It is possible to relate chi e to molecular properties of the substance, but we shall not pursue that here. We can relate this susceptibility to properties of a substance, like molecular properties of a substance, but that is not part of physics, at least for now. The question is, how does the polarized dielectric modify the original electric field inside it? Let us consider for simply a rectangular dielectric slab placed in uniform electric field, external field E0 parallel to two of its faces. The field causes a uniform polarization P of the dielectric. Thus, every volume element delta V of the slab has a dipole moment P delta V, because P by V, anyway, in the direction of the field, the volume element delta V is macroscopically small but contains a very large number of molecular dipoles. Anywhere inside the dielectric, the volume element delta V has no net charge, though it has net dipole moment. This is because the positive charge of one dipole sits close to the negative charge of the adjacent dipole. However, its surface of the dielectric normal to the electric field. There is evidently a net charge density as seen in figure 2.23. Uniformly polarized dielectric amounts to induced surface charge density but no volume charge density. there is a surface charge density. Yes, the surface charge density is because of these plus charges and these minus charges. These charges provided the surface charge density. And here, since positive negative, they will cancel each other, but at the surface there is only one charge, which is positive or negative this side. So here it is a positive surface charge density, whereas here it is a negative surface charge density. And the external electric field is this. Wait, no, yes, the external electric field is this side and the dipole moment is this side. The positive ends of dipoles remain unneutralized at the right surface and negative ends at the left surface. The unbalanced charges are the induced charges due to the external field. Thus, the polarized dielectric is equivalent to two charged surfaces with induced charge densities, say delta p, sigma p and minus sigma p. Clearly, the field produced by these surfaces, surface charges, opposes the external field. The total field in the dielectric is thereby reduced. From the case when no dielectric is present, we should note that the surface charge density plus or minus sigma p arises from bound, not free charges in the dielectric. Here we see that not the molecules are and not the individual charge carriers are getting arranged, but the total molecule itself is changing in arrangement. They are orienting themselves in such a way that the charges are aligning. And by keeping an by keeping a dielectric substance in between these two molecules, we are essentially reducing the electric field, because we are inducing a internal electric field. In case of a conductor, it will completely cancel out, but in case of a dielectric, that is not the case, and we are actually creating a induced electric field, and this will be lesser than the external electric field, and the total electric field is reduced, but it is not completely cancelled out like in conductors. And two charged surfaces which create a charge density of plus or minus sigma p. Now let's go to one of the main topics of this chapter. In the topic, it's in the main subject, main chapter name itself, potential, electrostatic potential and capacitance. Let's see about capacitors and capacitance. This is about more pages to go, including summary and including exercises. Capacitors and capacitance. Capacitor is a system of two conductors separated by an insulator. Figure 2.24. A system of two conductors separated by an insulator to form a capacitor. These are two conductors, and this is most possibly the insulator, what is in the present in the middle. And this charge is having a charge of Q, and this is having a charge of minus Q, and due to the attraction they are present in these edges here. Separated by an insulator. The conductors have charges, say Q1 and Q2, and potentials V1 and V2. Usually in practice, the two conductors have charges Q and minus Q with potential difference V equals V1 minus V2 between them. We shall consider only this kind of charge configuration of the capacitor. Even a single conductor can be used as a capacitor by assuming the other at infinity. Assuming the other to be at infinity. Okay. Unknown conductor. Okay. Conductors may be so charged by connecting them to two terminals of a battery. Q is called the charge of the capacitor, though this in fact is a charge of one of the conductors. The total charge of the capacitor will be 0. The electric field in the region between the conductors is proportional to the charge Q. As higher the charge Q, higher the electric field. That is, if the charge on the capacitor is, say, doubled, the electric field will also be doubled at every point. This follows from direct proportionality between field and charge implied by Coulomb's law and superposition principle. Now, potential difference V is the work done per unit positive charge in taking a small test charge from conductor 2 to 1 against the field consequently. Now, potential difference V is the work done per unit positive charge in taking a small test charge from the conductor 2 to 1 against the electric field. V is also proportional to Q, and higher the Q, higher the potential. The potential difference. Ratio of Q by V is a constant. Capacitance equals Q by V. The constant C is called capacitance of the capacitor. C is independent of Q or V as stated above. The capacitance depends only on the geometrical configuration, shape, size, separation of the two conductors, of the system of two conductors. As we shall see later, it also depends on the nature of the insulator dielectric separating the two conductors. The SI unit of capacitance is farad. 1 coulomb volt or 1 farad. 1 farad equals 1 coulomb per volt. A capacitor with fixed capacitance is symbolically shown as with two equal vertical lines joined by two horizontal lines, while the one with variable capacitance is shown as this. This is the same case as resistance. How resistance, normal resistance is shown as like this, and a rheostat or a variable resistance is shown like this. This is a capacitor. Equation 2.38 C equals Q by. Let's read the paragraph again. A capacitor is a system of two conductors separated by an insulator. The conductors have charges, say Q1 and Q2, and potentials V1 and V2. Usually in practice, the two conductors have charges Q and minus Q, with potential difference V equals V1 minus V2 between them. We shall consider only this kind of charge configuration of the capacitor. Even a single conductor can be used as a capacitor by assuming the other at infinity. The conductor may be so charged by connecting them to two terminals of a battery. Q is called the charge of the capacitor. Positive charge is called the charge of the capacitor, though this in fact is the charge of one of the conductors. The total charge of the capacitor is zero. The electric field in the region between the conductors is proportional to charge Q. That is, if the charge on the capacitor is, say, doubled, basically they are saying capital Q is directly proportional to electric field. As Q increases, electric field also increases. This is also same case for potential. Electric field will also be doubled if capital Q is doubled. This follows from direct proportionality between field and charge implied by Coulomb's law and the superposition principle. Now, positive charge is taking a small test charge. Now the work done, potential difference V, is the work done per unit positive charge in taking a small test charge from the conductor 2 to 1 against the field consequently. Taking a small test charge from the negative conductor minus Q to plus Q conductor, which is the first conductor, conductor 1, taking a small charge from conductor 2 to conductor 1 against the electric field. The work done in doing this is what we call as potential. And consequently, V is also proportional to Q, which I wrote here. Q is directly proportional to V. The ratio Q by V is a constant. C equals Q by V. The constant C is what we call as capacitance of the capacitor. C is independent of Q or V. As stated above, the capacitance C depends only on the geometrical configuration, meaning the distance between the two, the two plates or the two conductors, the shape and size of the conductors, the area of the conductors, and such. Of the system of two conductors, as we shall see later, it also depends on the nature of the dielectric placed between. It can be polar, non-polar, or the conducting effect. We saw that based on the nature of the conductor, the dielectric, the amount of the electric field reduced also varies. The nature of the insulator dielectric separating the two conductors. The SI unit of the capacitance is farad. 1 farad equals 1 coulomb per volt, or 1 farad equals 1 coulomb 1 C per V. A capacitor with fixed capacitance is symbolically shown as this symbol, using this symbol, and this is variable capacitor with variable capacitance, and this is a resistance with fixed resistance, and this is a rheostat with variable resistance. Equation 2.38, basically C equals Q by V. This can also be pronounced as farad, as in Faraday, but it depends. This equation shows that for a large C, V is small for a given Q. Shows that for large C, V is small for a given Q. If capacitance is large, we can say the potential difference is less and the charge of the capacitor is really high. This means a capacitor with a large capacitance can hold large amount of charge Q at relatively small V. This means a capacitor with large capacitance can hold large amount of charge Q at a relatively small V. This is of practical importance. High potential difference implies strong electric field around the conductors. A strong electric field can ionize the surrounding air and accelerate the charges, so produce to the oppositely charged plates. Thereby neutralizing the charge on the capacitor plates, at least partly. In other words, the charge of the capacitor leaks away due to the reduction in insulating power of the intervening medium. So basically, for a capacitance or capacitor, this is the plus and this is the minus. The dielectric is placed in between and the electric field is in this side. For a capacitor having high capacitance, C is capacitor has high capacitance, then we can say that it has relatively high charge at low potential. In such a case, if there is high potential, then let's assume there is high potential meaning particles will flow from low potential to high potential, then air will be ionized and negative particles will immediately go to the positive and this should be the negative. Positive particles go here, negative particles from the air go here and reduce the charge or neutralize the charge on the capacitor plates. That is what they are saying in the paragraph. The charge of the capacitor leaks away due to the reduction in insulating power of the intervening medium. The maximum electric field that a dielectric medium can withstand without breakdown of its insulating property is called a dielectric strength. For air, it is about 3 into 10 power 6 volt per meter. For this much electric field, the air won't be, this braking is nothing but, in cases of normally particles, let's assume for a polar particle it will be something like this. If there is an electric field applied, let's assume this is a positive and this is a negative, and let's assume it is a less electric field, it will, or a normal strength electric field, it will stretch like this. And as we keep on increasing this electric field, for air, like let's say for this medium is air, and we reached, the electric field reached 3 into 10 power 6 volt per meter. This is the electric field reached. Then what will happen is, this will stretch so much that it will lose this like ionizing property, like insulating property, and become free ions. In such a case, it's not an insulator anymore. It was an insulator because the charges were bound and it could not be separated. But when this happens, it is broken. In such a case, the medium loses the insulating property. The electric field at which this property, till which this insulating property is retained, is what we call dielectric strength. For a separation between conductors of the order 1 centimeter or so, this field corresponds to a potential difference of 3 into 10 power 4 volts between the conductors. Basically, this is when this distance is 1 meter, but as the meter is converted into centimeter, it will be 3 into 10 power 6 by 10 power 2, so it will be 3 into 10 power 4 volts. So you can say that as there is it is inversely proportional to radius. As radius decreases, it is directly proportional to radius. As radius decreases, the dielectric strength also decreases. Thus, for a capacitor to store a large amount of charge without leaking, its capacitance should be high enough so that the potential difference and hence the electric field do not exceed the breakdown limits. Put differently, there is a limit to the amount of charge that can be stored on a given capacitor without significant leaking. In practice, a farad is a very big unit. The common units are its submultiples: 1 microfarad, 1 nanofarad, 1 picofarad, etc. Besides its uses in storing charge, a capacitor is a key element most of circuits with important functions, which will be described in chapter 7. The parallel, which is one of the topics which we'll be studying here, is the parallel plate capacitor. A parallel plate capacitor consists of two large plain parallel conducting plates separated by a small distance. We first take the intervening medium between the plates to be a vacuum. Let's see the parallel plate capacitor. It has a surface charge density. As we saw before, this is the electric field direction. This is the area of the parallel plate capacitor, and d is the distance between them. And the insulating, the dielectric substance we take is first is a vacuum. The effect of dielectric medium between the parallel plate is discussed in next section. Let A be the area of each plate and D be the separation between them. The two plates have charges Q and minus Q. Since D is much smaller than the inner dimension of the plates, D square is much smaller than A. We can use the result on electric field by an infinite plane sheet of uniform surface charge density. Plate 1 has a surface charge density Q by A, and plate 2 has a surface charge density minus sigma. Using the electric field in different regions is outer region above the plate, E equals sigma by 2 pi epsilon naught. Outer region above the plate, it will be 0. Outer region 2, region below the plate, here as well it is 0. Inner region between the plates 1 and 2, the electric field due to the charge plates add up, giving E equals sigma by epsilon naught, which we can write as Q by epsilon naught A, Q by A times epsilon naught, or 1 by epsilon naught times Q by A. The direction of the electric field is from positive to the negative plate. Thus, the electric field is localized between the two plates and is uniform throughout. For plates with finite area, this will not be true. Near the outer boundaries of the plate, the field lines bend outward at the edges, an effect called fringing of the field. By some token, sigma will not be strictly uniform on the entire plate. E and sigma are related by the equation 2.35. However, for d square much lesser than the area, these effects can be ignored in the regions sufficiently far from the edges, and the field there is given by equation 2.41. Now for uniform electric field, potential difference is simply the electric field times the distance between the plates. EL, V equals EL. Now there is a special effect that they defined here. When capacitors, the electric fields bend outside, and when this is finite area and not infinite area, outward at the edges, an effect called fringing of the field is produced. This is what we call the fringing of the field. And the charge density will also be not uniform throughout the entire plate. This is a realistic situation. And using V equals EL, where L is D, the distance between the two parallel plates, we can take 1 by epsilon naught QD by A. The capacitance C of the parallel plate capacitor is then C equals Q by A epsilon naught A by D. As for how we got this, maybe we substitute it here, Q by V 1 by epsilon naught QD by A, Q cancels, so it will be epsilon naught, no, not D, epsilon naught A by D. Is it what we got here? Yes. So the capacitance will be epsilon naught A by D from the equation 1 by epsilon naught QD by A. Let's read the paragraph again. The electric field for an infinite conductor, like infinitely long sheet, it will be the outside the conductor, both regions it will be 0, but inside it will be Q by epsilon naught A. But how we got epsilon naught E equals epsilon naught, I mean charge density by 2 epsilon naught is this is similar to the Gauss law. So 2EA equals Q by epsilon naught, where 2A must be equal to E times A is electric flux. So when we take two surfaces, maybe we will get 2 times EA, where EA is electric flux. When we take two surfaces, maybe we will get 2 times EA, which is equal to the total electric flux. In such a case, if you want to find the electric field equals Q by 2 epsilon naught A, and we can write Q by A as charge density, so Q 2 epsilon naught. Maybe this is the reason we got such a formula that E equals sigma by 2 epsilon naught. Basically, I believe that is the case. And electric field value here, how they got E equals is 1 by Q by epsilon naught is Q by epsilon naught A is basically from this equation. Maybe they are taking for a single plate, so 2 vanished. No, wait. The total electric field, if we add up, then it will be Q by epsilon naught A. That is the reason here we took it as Q by epsilon naught A times T, where the potential is QD by epsilon naught A. Not totally convinced, but it seems I'm finding the relation. Let's read the paragraph again. The direction of electric field is from positive to the negative plate. Thus, the electric field is localized between the two plates and is uniform throughout. For plates with finite area, this will not be true. Near the outer boundaries of the plate, the field lines will bend outward and edges an effect called fringing of the field by some token. Sigma charge density will not strictly be uniform on the entire plate. E and sigma are rated by equation 2.35. However, for d square smaller than A, these effects can be ignored in the region sufficiently far from edges, and the field there is given by 2.41. The place that is. Let me derive it again. For parallel plate capacitors, plus plus and minus minus minus. In such a case where we take area, this is the area to be greater than, much greater than d square, the distance extremely close. And in such a case, if we want to find out electric field, and electric field will be for one parallel plate capacitor for one half, electric flux they found out first outside, which they found out as, wait, let's just, for one plate it is q epsilon naught q by 2 epsilon naught, and this is not E, this is EA cos theta is EA cos theta, where cos I believe is 0, cos 0 degrees, so it is 1. So EA, using the Gauss law, epsilon naught equals EA equals q by 2 epsilon naught. This 2 came because we are considering a single parallel plate here. So in such a case, the electric field for a single will be q by 2 epsilon naught A, and this will be E equals sigma by 2 epsilon naught. This is just for remembering and might not be true. And for the total electric field inside, it will be epsilon naught by 2, sigma by 2 epsilon naught by sigma by 2 epsilon naught. It will be 2 sigma by 2 epsilon naught. We can write it as q epsilon naught by A, which is the electric field. And potential between the two parallel plate capacitors, if we want to find the potential, we know that E equals V by L, or delta V by delta L, and V equals E times L. In such a case, we can substitute the value here, where q by epsilon naught A times D is the potential. Yes, this is a potential that they derived in the textbook. The capacitance C, and as for substituting in the final equation, where we got both the values of Q and V, the capacitance equals Q by V, so C equals Q by V value, QD by epsilon naught A, Q cancel, C equals epsilon naught A by D, where epsilon naught is constant and C equals epsilon naught A by D, depends on the area by distance. As the distance increases, as we can, from this equation we can say it is inversely proportional to D and it is directly proportional to A. As area increases and distance decreases, capacitance increases. which, as expected, depends only on the geometry of the system. For typical values like A equals 1 meter square, D equals 1 mm, we get C equals, this is the value of the epsilon naught, 1 meter square by 10 power minus 3 meter, 1 millimeter, this is the distance. Then total capacitance will be 8.85 nanofarad. You can check that if 1F equals 1 coulomb per volt equals 1 coulomb, this value and this shows that 1F is too big a unit in practice. As remarked earlier, another way of seeing the bigness of 1F is to calculate the area of plates needed to have C equals 1F for a separation of say 1 centimeter. Then the area equals CD by epsilon naught, which is 10 power 9 meter square, which is a plate about 30 kilometer in length and breadth. 30 kilometers. No building doesn't reach that high. Even the Mount Everest is smaller than that. Effect of dielectric on capacitance. Effect of the next topic, effect of dielectric on capacitance. With the understanding of the behavior of dielectrics in external field developed in section 2.10, let us see how the capacitance of a parallel plate capacitor is modified when a dielectric is present. As before, we have two large plates, each of area A separated by a distance d. The charge on two plates is plus or minus q, corresponding to the charge density plus or minus sigma, with sigma equals q by a, where there is a vacuum between the plates. Before, whatever we are seeing here, there is vacuum between the plates, but here we are taking a dielectric material. Electric field equals sigma by epsilon naught. I'll be back in a few minutes. With the understanding of the behavior of dielectrics in an external field developed in section 2.10, let us see how capacitance of a parallel plate capacitor is modified when a dielectric is present. As before, we have two large plates, each of area A, separated by a distance d. The charge on the plates is plus or minus q, corresponding to the charge density plus or minus sigma, with sigma equals q by a when there is vacuum between the plates. E equals sigma by epsilon naught, and the potential difference V naught is V naught equals E naught d. The capacitance C naught in this case equals C naught equals Q by V naught, which is equals to epsilon naught A by d. Consider next a dielectric inserted between the plates, fully occupying the intervening region. The dielectric is polarized by the field, and as explained in section 2.10, the effect is equivalent to two charged sheets at the surface of the dielectric normal to the field. With the surface charge densities sigma p and minus sigma p, the electric field in the dielectric then corresponds to the case when the net surface charge density on the plates is plus or minus sigma p, that is E equals sigma minus sigma p by epsilon naught. Consider net dielectric inserted between the plates, fully occupying the intervening region. The dielectric is polarized by the field, and as explained in section 2.10, the effect is equivalent to two charge sheets at surfaces of dielectric normal to the field with surface charge densities. Electric field in the dielectric corresponding to the case where net surface charge density on the plates is plus or minus. Okay. This sigma p is the polarized charge density. So as the dielectric is polarized, there are two charge densities on the surface, and here the electric field equals, we know this electric field is sigma by epsilon naught, so here the difference we are taking, so that the potential difference across the plates is V equals CD, sigma minus sigma PD. The potential difference across the plates is sigma minus 6 sigma p by epsilon naught t times t. For linear dielectrics meaning we expect sigma p to be proportional to epsilon naught, E naught. As the electric field externally increases, the polarization charge density also increases. This is the isotropic linear dielectrics we studied before in the topic capacitors, or no, not capacitors, but dielectrics and polarization, where isotropic linear dielectrics, they have the polarization or dipole moment vector to be proportional to E naught vector, the electric field, that is to sigma. Thus sigma minus sigma p is proportional to sigma, and we can write sigma minus sigma p equals sigma by k, where k is a constant characteristic of dielectric. Clearly k is greater than 1. They have instead of reducing the charge, we are actually dividing the main sigma by K, a constant characteristic of the dielectric. It needs to be greater than 1, so the actual value of this will reduce. That doesn't mean it should be 0 point something, it is just reduced. V equals sigma d by epsilon naught K. Basically epsilon naught, the electric potential times T became sigma by K by sigma by K epsilon naught times T, which we can write sigma as Q by A. This will be the final formula for potential, and capacitance, if we substitute in this formula, epsilon naught Ka by D, the capacitance C with that between the plates, is then epsilon naught Ka by D. As we can say here that as the higher the K, the higher the C value. As here the difference the product delta K is called the permittivity of the medium and is denoted by epsilon. Epsilon equals epsilon naught K. For vacuum, K equals 1 and epsilon equals epsilon naught. Epsilon is called the permittivity of the vacuum or free space. The dimensionless ratio K equals epsilon per medium per epsilon naught is called the dielectric constants of a substance. As remarked before, from equation 2.49 it is clear that K is greater than 1. From equation 2.46 and 2.51, K equals C by C naught. Thus the dielectric constants of a substance is the factor greater than 1 by which the capacitance increases from its vacuum value when the dielectric is inserted fully between the plates of a capacitor. Though we arrived at equation 2.54 for the case of parallel plate capacitor, it holds good for any type of capacitor and can in fact be viewed in general as a definition of the dielectric constants of a substance. Let's see this. A slab of material of dielectric constant K has the same area as the plates of parallel plate capacitor but has a thickness 3 by 4 D, where D is the separation of the plates. How is the capacitance change when its slab is inserted between the plates? Let epsilon naught equals, E naught equals V naught by D be the electric field between the plates when there is no dielectric and the potential difference is V naught. If the dielectric is now inserted, the electric field in the dielectric will be E equals epsilon naught, E naught by K. The potential difference will then be V equals epsilon naught 1 by 4D plus epsilon naught by E naught by K 3 by 4D. As potential is a scalar quantity, we are individually adding the individual potentials. As 1 by 4th of the distance has no dielectric material, we take it as epsilon naught and there is K equals 1, and in this case it is as such, and we both add them. And everything except K is common, and K and constant is common. Epsilon naught D 1 by 4 plus 3 by 4K. V naught equals K plus 3 by 4K. The potential difference decreases by the factor K plus 3 by 4K while the free charge on the plate remains unchanged. The capacitance thus increases. as we substitute in the formula Q by V, the potential will be V equals Q by not potential, sorry. The capacitance will be Q by V, and Q by V value is V naught times K plus 3 by 4K. It can be written as Q by V naught, which is the original capacitance, times 4K by K plus 3. So you can say C equals the change, this is the final, equals 4K by K plus 3 times the initial capacitance, which we can write as CO or CI. In the next topic, it is combination of capacitors. Combination of capacitors, actually we can write it which is directly different or reverse of the resistances. As resistances, if corrected in case of resistances, if connected in series, then the total resistance will be equals R1 plus R2. This is in series. In case of parallel, combination, resistances will be then the total resistance here will be 1 by R total equals 1 by R1 plus 1 by R2, which can be written as 1 by RT equals R1 plus R2 by R1 R2, which we can write it as the total resistance being equal to RT equals R1 R2 by R1 plus R2. This is the total resistance in case of a parallel combination. Exactly reverse in case of capacitors. Capacitors in series, C total will be equal to 1 by C total will be equal to 1 by C1 plus 1 by C2, or C total will be C1 C2 by C1 plus C2, and in case of parallel, CT equals in case of parallel C1 C2, C total will be equals C1 plus C2. Combination of two capacitors in series and combination of n capacitors in series. It seems very confusing, but these are the positive charge, negative charges of the plates. Combination of capacitors. We can combine several capacitors of capacitance C1, C2, Cn to obtain a system with some effective capacitance C. The effective capacitance depends on the way the individual capacitors are combined. Two simple possibilities are discussed below. Capacitors in series. Figure 2.26 shows capacitors C1 and C2 combined in series. These pictures. The left plate C1 and the right plate C2 are connected to two terminals of a battery and have charges Q and minus Q respectively. It then follows that the right plate of C1 has charge minus Q and the left plate of C2 has charge Q. If this was not so, the net charge on each capacitor would not be zero. This would result in an electric field in a conductor connecting C1 and C2. Charge would flow until the net charge on both C1 and C2 is zero. There is no electric field in the conductor connecting C1 and C2. Thus, due to the electric field, as the charge is exhausted, or where the net charge is on both C1 and C2 is zero, the charge will continue to flow. There is no electric field in the conductor connecting C1 and C2. Thus, in the series combination, charges on the two plates are same on each capacitor. The total potential drop V across the combination is the sum of potential drops V1, V2 across C1 and C2 respectively. V equals V1 plus V2, Q by C1 plus Q by C2. We are using the formula C equals Q by V and V equals C by V equals Q by C. V by Q equals 1 by C plus 1 by C2. Now we can regard the combination as an effective capacitor with charge Q and potential difference V. The effective capacitance of the combination is C equals Q by V. 2.57 to 2.56 we compare and we obtain that 1 by C equals 1 by C1 plus 1 by C2. The proof clearly goes through for any number of capacitor arranged in a similar way. Equation 2.55 for n capacitor arranged in series generalizes following the same steps. For the case 2 capacitors, we get the general formula of the effective capacitance of series capacitors. And capacitors in parallel, this is the image, shows two capacitors arranged in this case. The same potential difference is applied across the both capacitors, but plate charges capacitor and the plate charge plus or minus Q2 are not necessarily the same. Q1 equals C1, Q2 equals C2V, Potential will be same. The equivalent capacitor is 1 with the charge Q equals Q1 plus Q2. The potential difference equal Q equals, when we are equating it to potential difference, then Q equals CV equals C1V plus C2V. The effective capacitance C is equation from this equation, C equals C plus C1 plus C2. The general formula for effective capacitance C for the parallel combination for n capacitors follows similarly. Q equals Q1 plus Q2 plus Qn, and CV equals C1V plus C2V plus CNV, which gives C plus C2 plus Cn. A network of 410 10 microfarad capacitors is connected to 500 volt supply as shown in figure 2.29. Determine A, the equivalent capacitance of the network, and B, the charge on each capacitor. Note the charge on a capacitor is the charge on the plate with higher potential equal to the opposite charge on the plate with the lower potential. In the given network, C1, C2, C3 are connected in series equals 10 by 3. The network has C dash and C4 connected. The next topic, the energy stored in a capacitor. A capacitor, as we have seen above, the system of two conductors with charges Q and minus Q. To determine the energy stored in this configuration, consider initially two uncharged conductors 1 and 2. Imagine next a process of transferring charge from conductor 2 to conductor 1. Bit by bit, so that at the end conductor 1 gets a charge of Q, and by charge conservation conductor 2 has a charge of minus Q at the end. In transferring positive charge from conductor 2 to 1, work will be done externally, since at any stage conductor 1 is at higher potential than the conductor 2. To calculate the work done total, we must calculate the work done in a small step involving transfer of infinitesimal, vanishingly small amount of charge, considering an intermediate situation when the conductors 1 and 2 have charges Q dash and minus Q dash respectively. At this stage, the potential difference V dash between the conductors 1 to 2 is Q dash by C, where C is the capacitance of the system. Next, imagine that a small charge delta Q dash is transferred from conductor 2 to 1. Work done in this step, delta W resulting in charge Q dash on conductor 1 increasing Q dash plus delta Q dash is given by delta W equals V dash delta Q dash equals Q dash by C delta Q dash. Integrating this equation from 0 to the total charge, we will get Q square by 2C. We can write the final result in different ways. W equals Q square by 2C, 1 by 2 CV square, 1 by 2 QV. Since the electrostatic potential is conservative, this work is stored in the form of potential energy of the system. For the same reason, the final result for potential energy is independent of the manner in which the charge configuration of the capacitor is built up. When capacitor discharges, the stored up energy is released. It is possible to view the potential energy of the capacitor as stored in the electric field between the plates. To see this, consider for simplicity a parallel plate capacitor for area A of each plate and separation D between the plates. Energy stored in the plates, capacitor 1 by 2 equals 1 by 2 Q square by C equals, we can write A alpha whole square by 2 times d epsilon naught a. We are writing C as d by epsilon naught a, 1 by C as d epsilon v by epsilon naught a, and the charge density is related to the electric field E between the plates. E equals sigma epsilon naught from equation 2.70 and 2.71. We get the energy stored in the capacitor equals 1 by 2 epsilon naught E square times AD. Now note that AD is the volume of the region between the plates. Area times length is volume. Electric field alone exists. If we define energy density as energy stored per unit volume of space, shows that energy density of the electric field is U equals 1 by 2 epsilon naught E square. Though we derived equation 2.73 for the case of a parallel plate capacitor, the result on energy density of an electric field is in fact very general and holds true for electric field due to any configuration of charges. I will not be doing this sum right now. I hope to do a revision on the capacitor once again, as I did not go too far into the understanding. So with this first NCERT revision of chapter Electrostatic Potential and Capacitance is completed. With this, I will be ending the stream.